धन संपदः Shatru Buddhi Vinasaya Deepa Jyoti Namostute. I fold my hands before the light that brings prosperity, auspiciousness, good health, abundance of wealth and destruction of the enemy's intellect. Om Shri Sai Ram, offering myself to the one who is the light of the universe. A very warm welcome to all of you in this afternoon session of the second edition of Professor M.K. Sundaresan Memorial Lecture Series, organized by the Department of Physics, Sri Sathya Institute of Higher Learning, on recent trends in photonics. In this process of getting enlightened with the knowledge of light, I invite our next speaker, Professor Sai Santosh Kumar Ravi, to shed light on excited state dynamics and all optical modulation investigations of novel organic materials. Professor Sai Santosh Kumar Ravi is a distinguished professor in the Department of Physics, IIT Hyderabad. He completed his BSc and MSc in Physics with Photonics specialization from Sri Sathya Sai Institute of Higher Learning, followed by a Ph.D. from the University of Hyderabad. He then went on to do his postdoctoral research at Politecnico di Milano and the Center for Nanoscience and Technology, Italian Institute of Technology, Milan. Professor Ravi's research focuses on ultrafast spectroscopy and organic photovoltaics, investigating excited state dynamics of organic molecules and contributing to advancements in organic solar cells and optoelectronic devices. His notable achievements include being a Fellow of the Royal Society of Chemistry, Associate Editor of Optical Materials Journal, Member of the National Academy of Science India, Member of the Indian National Young Academy of Science, and more. He has received prestigious fellowships like the Bhaskara Advanced Solar Energy Fellowship and FAPESP Visiting Researcher Fellowship. Professor Ravi's research has been published extensively with over 110 articles in peer-reviewed international journals and conferences, with an impressive H index of 26 and approximately 3,000 citations. Furthermore, he has received multiple honors, including being an Optical Society of America senior member, Associate Fellow of Telangana Academy of Sciences, winner of the Young Scientist Award in Physics in 2008, among others. Professor Ravi's contribution to the field are highly regarded, making him a respected figure in the scientific community. Join me in welcoming Professor Sai Santosh Kumar Ravi. Sir will be speaking to us on the topic Excited State Dynamics and All Optical Modulation Investigations of Novel Organic Materials. Professor Sai Santosh Kumar Ravi.
Guru Brahma, Guru Vishnu, Guru Devo Maheshwara, Guru Sakshat Parabrahma, Tasmai Shri Guruve Namah. Invoking Swami's blessings, respected teachers, I feel very small here in front of the teachers who taught me the basics of physics, and I'm I think it's my way to say gratitude to your hard work. And I hope the work which I present today would be useful to the society, as well as something which students can learn from it. I would like to thank all the teachers who taught me during my time here, and I continue to grow because of your hard work and goodwill. Sairam. So today, I would present my work on with this lecture series titled Recent Trends in Photonics. I thought I would speak more on the excited state dynamics and optical modulation investigations in novel organic materials. Now, this is little away from what we have been hearing from morning, where we had stalwart speaking on condensed matter physics. This is bordering towards physical chemistry and bit of energy kind of work. And I would present more work on the various spectroscopy studies for this energy materials. So, just to reminisce myself, these pictures are what were taken 2004, exactly 20 years back. And I was finishing my second MSc, memorable days. And just to digress a bit, after this meeting, our GATE results came, and in our batch, the topper in physics was 11th rank, topper in chemistry was the second rank, and all of us were happy, and Swami was also excited that there are rankers in the batch. And so Swami said, okay, who are the rankers here? And all the students who got GATE ranks stood up, naturally. Now there are too many people and no one knows where to stop. Then one rule came, all who got above 90 percentile should stand. And I got 90.85 percentile. And I was the last guy in the entire row to stand and wait for Swami. Swami kept asking from the topmost person, and he came all the way till here, and I was the last guy. And in a way, it is good because he had no one to talk after me, and he asked, "What are you going to do?" I mean, all of us were thinking MTech or research, but I was not sure. In fact, I wanted to ask Swami's opinion, and I said, "Swami, I will do PhD or research." Then Swami asked, "What is it? A PhD or research?" Then he said, "Rendu okate kada." Then I realized the mistake. "Yes, Swami, you tell me where I should do." He said, "Okay, do research." Then he looked behind and he was calling one of the commerce faculty. He said, "Swami, in physics department, Swami." "Avuna? Aithe bayatiki vellipo, Swami chuskuntaru." And I think with that blessings, I'm what I am, and thanks to Swami. Yeah. So coming to the talk, I would like to start with acknowledging the funding sources, because we need a lot of money for doing research, and I thank the funding sources. We have DST, CSR, BRICS, BRNS, CAT grant, and my group members, and they are the ones who do all the work. We have 4 students who graduated, and I'm presenting work of one of the students, Chinmay, today. And the other work is mainly done by Sudhanshu and Shoaib. They'll be presenting. They're working on things. So we have 2 types of students. One specifically working on the spectroscopy aspects of it, other working on the devices aspect of it, so that we have all the understanding in the group. And this is the big network we have, international and national network. And I would like to thank Professor Peng, whose samples I'm using today, and Professor Venugopal Rao and Giribabu, who are the collaborators in University of Hyderabad, to give me the access to the laser when we didn't have the laser in the lab. Right, so we have facilities ranging from solar cell fabrication to luminescence spectroscopy. This is the, where is it? I'm sorry, yeah. So this is a luminescence spectrometer where you can go low temperature PL, pump probe, and all the facilities which are required to do organic solar cells, more or less. Right, so my main expertise is with ultrafast spectroscopy studies. So we call ourselves Ultrafast Photonics and Photophysics Laboratory. And the core expertise with which I did my PhD and the postdoc are in ultrafast spectroscopy and nonlinear optics. And we have done quite a lot of work, extensive work in these fields. With the new instrument which we got, we also moved into the latest materials, which are the halide perovskites. And under halide perovskites, we started looking at lead-free perovskites, low-dimensional perovskites, and various organic molecules. Bit of ceramics also I ventured into it. When we began, we worked on rare earth-doped, lead-free perovskite oxides. Then last 4 years, we put a lot of efforts to begin our own device lab, because this is not my core strength. I started learning with the students, and we ventured into dye-sensitized solar cell, which is the easiest to do. And now we also started working on the bulk heterojunction solar cells, and there's a patent which is there. I'll just briefly talk about that soon. Right, so major direction of our group is into energy, and we use all I know into this domain. So starting from ultrafast transient absorption spectroscopy, which I would start working on, talk on that. So we worked on the, one of the earliest work was to demonstrate the so-called multi-step electron injection, which was, people thought of it, but there was no demonstration. So we demonstrated that. We also work on various new molecules which change their shape in the excited state, which, for example, this is the twisted intramolecular charge transfer characteristics, where the molecule the torsional inversion happens in the molecule, and we can look into that. Just two of them. And we demonstrated tunable NIR emission in basic titania. Titania is well-known material, and by doping erbium and Nd, co-doping it, we could tune the emission. And titania being a biocompatible material, this has very good potential in the bioimaging. And this is a recent work in optical detectors where we worked on the lead-free perovskites. This is low temperature PL studies we have done. And in solar cells, we demonstrated eco-friendly kumkum-based DSSC. Kumkum-based is a kumkum with the kumkum which we all put, right? So the way it is done is, there is a dye called, it's a magenta dye, and they mix with turmeric and they mill it together. And that gives the kumkum color, right? So what we did, we picked up the dye which gives that color, it's in magenta and later, and we demonstrated. I have one slide to it to show that. We also started working on perovskite solar cells, which is the latest one, and that is the solar energy work in 2023, last year. And also this same, the idea is the same. You have titania and donor acceptor systems, which can be used for solar cells and also used for the water splitting. So same systems, we also demonstrated water splitting behavior for hydrogen evolution. And recently, which is one of the directions which we are really focusing, is in indoor photovoltaics. And just to say the difference between indoor photovoltaics and solar photovoltaics, as the name suggests, solar requires sun, where you put your solar cell under the sun and you extract current out of it. On the other hand, indoor photovoltaics work with a concept where it would harvest the light indoor, with indoor lights, be it your LED, CFL, diffused light, just what is diffusing inside the room. So this kind of material, this kind of devices are interesting because one of the main issues with the organic or emerging materials, not the inorganic silicon based or gallium arsenide based, is the stability. Now this, just like how if you put your jeans outside in the sun, within 2 days it starts bleaching. So organic systems, organic molecules cannot, organic dyes cannot survive this intense heat and sun. So they tend to lose their stability over the period of time. Of course, it is cheap, so you can always replace it with time, but the stability issue is still there, which cannot be solved because it's the inherent nature of the material. So we thought, why to put it out when organic systems are good enough to absorb so much of light, because their absorption coefficient is so strong compared to the silicon. Silicon is an indirect band gap system. So if it is absorbing so strong, so even with low amount of light is sufficient to generate the electron hole pairs. So with that idea, we wanted to push the indoor photovoltaics, and now it is actually being used quite often, quite a lot in various labs. And because with this kind of indoor photovoltaics, if you can get stable output in low light conditions, this is sufficient to power the IoT devices. We all talk about smart materials, smart devices. So these are all low power IoT devices, and this can be powered by these indoor photovoltaics. And that's the plan which we are having. So this is the paper which we published last year, and it showed efficiency of 14%. Now we could demonstrate, I haven't published yet, it's about 20%, it's a demonstration work. Then this is the work I told you about, where we could thermally evaporate a solar cell. And it's not just one solar cell, there are 88 solar cells in that small module, which is sufficient. It's just like a 7.5 by, it's like a microscope slide, basic microscope slide, ITO substrate of course. This can light, okay? I'll just show that slide. Right, so quickly, because it is very interesting, I thought I'll present you the one slide on low cost aqueous dye sensor solar cell. So this sort of hits two birds with one stone. One is to use water-based electrolyte, which was a problem because water is supposed to be a killer of solar cells. People don't want water in their organic solar cells. It so happens that because this material dissolves in water, people thought it is counterintuitive to have water in the electrolyte. However, we figured out that only if you put water-based electrolyte, it works. And now, by having this water-based electrolyte, this particular system is robust, cheap. I just gave you the numbers which we have. The molecule costs 2.5 grams rupees per gram. The counter electrode is not platinum based but carbon paste, which is 1 rupee per centimeter square. It's a carbon cloth. And liquid electrolyte is KCl, potassium chloride solution, and very cheap, and it was giving 2.88%. Important point here is not to look at the efficiency. Of course, efficiency is very poor, but it paved a way in figuring out that yes, we can use Indian local dyes. We don't need to import a dye. That was the main contribution for us, and in fact, we have done this solar cell device work as well as the spectroscopy work to prove our point, and it got a lot of media attention. So I will not get into that. Then we talk about this thermally evaporated bulk heterojunction solar cell. No, bad life. This particular, we're talking about this life or this material, this was staying up to few weeks. Few weeks it would stay. The only problem with this device is electrolyte gets evaporated. That is all. So if you can pack well and put epoxy around it, it will stay. Because this dye is stable, and as I said, it cannot stay outside. It is indoor.
What is your electrode?
Carbon fabric.
Carbon fabric.
Carbon fabric.
And the
Basic
top,
carbon
top
fabric.
One, top electrode? Top electrode?
I cannot hear, sir.
No. What is your bottom electrode? What is your top electrode?
It is KCl solution with Fe2 plus Fe3 plus. Otherwise, in DSSC they use iodine based. So iodine is corrosive. So we replace that with that. So this Fe3 plus Fe2 plus comes from the concept of quantum dot solar cell. So it is not picked up from, it was just taken, borrowed from that concept and we put it here. That's the thing. Yeah. So this is the new work which we got it last year, where thermally evaporated bulk heterojunction solar cell. So this is organic solar cell kind of thing. And important difference between what is being done here is that normally people use solution based methodologies, processing, where they put, it's very simple. You take donor solution, acceptor solution, you mix it, stir it overnight, and you spin coat it. So that is your active layer. It's very 200 nanometers active layer, very good bulk heterojunction. But there is a lot of issues in terms of morphology. Anyway, the innovation here we did is we figured out a way to thermally co-evaporate the two donor acceptor. The reason why it is interesting is that moment you can thermally evaporate, you have the control over the evaporation in the area, which is not the case when you do a spin coating kind of, because spin coating by virtue of it, it just covers the whole thing. So one can put mask and figure out how to make a module, which is what we did it. So this is the module, 88 cell module. Okay, so 88 solar cells are there in that module. So now when you have 88 solar cells in that small slide, we put it under the sunlight in the terrace, and we got power output of 3.8 milliwatt. Okay, now 3.8 milliwatt is good enough to drive many low power electronics. So that is what is the idea, and we patented this. Right. Cell area is 0.3. It's about 3 mm by 3 mm. That's all. That's the optimum size. Below this, we lose at the area. It is not efficient anymore. Yeah. So efficiency is also not good, but yeah, that's fine. Now coming back to the main part of it, because I thought you're all sleeping, so I interest you with something applications before we go to boring spectroscopy. Okay, so now in this work, I present 3 different organic molecules, 2 porphyrins and 1 phthalocyanine. Okay, so this are used for photocatalysis, organic solar cells and diacetyl solar cell applications. And also we have used these molecules for the nonlinear optical application, which I would just present you on terms of the all optical modulation. So that is the end of it. I'll try to rush towards the end because if it's a repetition, I'll just rush over it. But overall, I'll try to put the whole thing in one perspective. Okay, so when I say excited dynamics, we have already heard about pump probes technique in the previous talk. I just quickly rush, brush you towards the idea of this term absorption, transient absorption spectroscopy. What is pump probe? Basically, idea is you have a sample, you pump the sample to an excited state, and you probe with a delayed broadband pulse. Why do we need to do that? And what we measure is the detection is delta T by T, which is the transmission of the probe in the presence of pump minus transmission of the probe in the absence of pump. Okay. Now, why we do it? The idea is simple. In the absence of pump, what transmits is simple ground state absorption. Because that's the idea, right? You send white light through a sample and you have detected whatever is transmitting is that which is absorbing, right? Which is not absorbed. So our interest is to look at the excited state dynamics, which means we need to access to these excited states in order to look at the absorption of it. How do we do that? So you pump it, you let the population go to an excited state. Now those states which are unpopulated the light doesn't see that, it just transmits. But once they are populated, the light would always see those things, right? And so the absorption happens. So one can use this idea to really look at the transmission changes in the excited state and follow the delay dynamics. Now, simple idea, if you take pump as IPU of term, it's a pulse, and you probe as something which is delayed by tau, okay, it's slightly delayed pulse, and the impulse response of the medium to be, A of t, then the pump induced variation of the probe is the convolution of the system response with the cross correlation of the pump and the probe. What it means is that as the pump and the probe correlate, because these are all time delayed experiments, okay, when they correlate, at the correlation the response of the system varies, okay. That variation of the response is now related to the cross correlation time, because if the cross correlation time is long, then everything that is happening within that cross correlation is averaged out. So all dynamical processes within the cross correlation time are averaged out, and so the best way to do these experiments are to use femtosecond pulse because they are short time, okay. Now femtosecond experiment is very simple. If you look at the final thing, which is pump and probe, just to reach this stage you got to delay pump and the probe, because if you take 100 femtosecond pulse, the footprint of the 100 femtosecond pulse is about 30 microns. Okay, now you want to match the pump and the probe to 30 microns path length delay, okay, and to achieve that one needs to have a little bit complicated setup as I showed here, but it is achievable. Once you do it, you can do the experiment. Now how do we look at the signal? And I just explain you from the point of view of the organic system, because that's what is the main interest here. Now if you take a material, any organic system, it would have its own ground state absorption and photoluminescence, okay. Now if you want to excite the system, where do you pump? You always try to pump at the absorption maxima. So when you pump with absorption maxima, what happens is the ground state, the population of the ground state goes to the excited state. I'm just giving a simple cartoon here. It can go to any S1, I don't care, okay. But right now, simple example, S1, S0 to S1, it goes singlet states. Now I come with a broadband probe and delay it. At time t equal to 0, what happens? This is what I see. Let's see, this is the broadband probe and it is covering the entire spectrum from visible to the whatever probe you want, length, near infrared or whatever. Now signals are three types. One, the part of the probe which overlaps with the ground state absorption. Okay, what happens now? When this probe, that part of the probe, where it sees that ground state, okay, that part, it sees less population in the ground state, and so the transmission increases, because of which the delta t by t is positive. I just showed you in terms of minus delta a by, it is differential absorption, so it is negative. So it is positive signal here. Similarly, when the part of the spectrum which corresponds to the photoluminescence, okay, so this would see the population in the excited state and kick off, giving to a stimulated emission event. So that also is addition. Stimulated emission is giving an additional photon, so the signal would be positive. And finally, which is most interesting to us, is the excited state S1 has its own absorption characteristics, and if a part of the probe overlaps with that absorption of that excited state, then the transmission is reduced, because a part of the probe is absorbed, the spectrum is absorbed, and that is what gives us the negative signal, okay, which we call as the photo-induced absorption. Okay, now if you track what happens in the excited state, a lot of information we can get. Again, let's looking at the simple idea of a organic system. You have in organic system singlets, triplets. So once it goes to a singlet state, excited singlet state, it can get the right absorption spectrum and get excited to a higher singlet, which we call as singlet exciton, or it can do the intersystem crossing and move, a population can get into the triplets, and once it goes to triplets, the triplet manifold starts getting absorbed. So we can also follow the triplet excitations. Otherwise, if the system loses an electron or gains an electron, it becomes charged. This charged material molecule would have its own absorption. Okay, now this charged, because it is happening in the excited state, can have its own absorption, and that can be tracked by this charge band. So overall, once we have the excited state spectrum, just by following the time duration of it, how the spectrum evolution is happening, how the kinetics are changing with time, can give us the overall information of the excited state. And that's the point which we do here. Okay, now this is, I think it's not clear here because of my bad resolution, but yeah, different processes. One is the internal conversion, vibration relaxation, intersystem crossing. All these processes have their own time scales, and by following those time scales and proper spectrum, one can access it. Okay, so how do we analyze the data? For that, we use the so-called, there's a global fitting. Okay, what is global fitting? I'll just come to it. So once you have the experiment, you get the entire spectrum. It's a 2D matrix. You get the spectrum at every time duration. Okay, at every delay of the probe, you get spectrum. So if you take the row as a spectrum, then the column would be the time kinetics, the kinetics of every wavelength. And that's what we do. So moment you get this 2D spectrum, okay, it's a 2D color map. You normally get, and it's a 2D matrix eventually. Looking at the individual wavelength kinetics would not give us any information. Okay, so to get a proper understanding of the system, single wavelength kinetics is useless. What we do is we look at the overall spectrum by itself. For that, we do this global analysis. What I say global analysis, like global, it's all the wavelengths which are there. The entire probe is now taken as the entire matrix, and we try to analyze the matrix by doing some photophysical modeling. When you do the photophysical modeling, you give some inputs, guess inputs, and you see how can we give this, given a guess input. Here a guess input would be typically rate constants, right? Or excited state rate constants. If I give a typical excited state rate constants as a guess and try to generate another 2D matrix which matches with exactly with the experimental data, that is my fitting. That's what we do. Okay? So you put the parameter. These parameters can be anything: conductivity scheme, initial time constants, quantum yield, anisotropy, any material property, photophysical system, any photophysical property, being absorption, emission, anisotropy, polarization studies, everything are the parameters now for this kinetic scheme. And once we have the scheme, then you can do the analysis. Okay, now you iterate it, and over the iteration, you end up getting the true numbers. Now that's how we do the final fit and the kinetics. So from mathematical, it is simple. If you simply take a case of a bilinear rate model, 3-component process, it's a 2-dimensional 2D matrix. You take a basis set of column and row, and you can get the entire spectrum. These are called species assisted decay spectrum, SADS and DADS. This can be obtained by the linear combination of all the row and column vectors. So that's how one can do the fitting and get information out of the material. Okay, so a lot of work we have here. Yes, so we try to keep the number of levels as low as possible, because as you increase the number of levels, fitting improves, but it becomes photophysically it is not possible. So we try to understand what material it is and then follow the Jablonski picture and use accordingly. So that is the only thing which we do, and a lot of work we have done. Probably I can share the works with you later. Throughout the bandwidth, and the more the bandwidth, the better it is. Sorry, sir? White light continuum. White light continuum. So we use the white light continuum in the visible and the probe and the IR. Okay. So that is the idea of the pump spectroscopy. Now I get into the molecular part, because this is also important to understand. Now, one of the molecules, the kind of molecules which we are interested in are those which have intramolecular charge transfer. What is intramolecular? So intermolecular is like, one molecule, other molecule. When the charge transfer happens from one molecule to other molecule, it is intermolecule. Now, intramolecule is an idea where the charge is shifting from one part of the molecule to the other part. Eventually, it is like electron cloud moving from one part to the other part. But this happens in the excited state, which means from a chemist point of view, you have highest occupied molecular orbital and lowest unoccupied molecular orbital. If you do this DFT and look at the electron cloud in HOMO level, it could be spread in one part of the molecule. In the excited state, the LUMO, the cloud would have been shifted to other part. So that is the idea of the intramolecular charge transfer. Okay. So organic pi systems, conventionally known as organic push-pull, because one is pushing the charge, other is pulling the charge. That's why they call push-pull. Are those in which donor-accept interaction, or the ICT, is responsible for generating the distinct optoelectronic properties. Okay. This is because of this absorption and the motion of the electron cloud, a lot of new optoelectronic properties can be obtained. Okay. So this is a DPHY, donor, acceptor, and they are separated by some pi spacer. Now this is a fundamental step for majority applications, OLEDs, OPVs, non-linear optics, a lot of things. And important point here is that the electron rich part to the electron, poor part, acceptor, they are the ones which play a crucial role. And anything that happens is the excited state. So in excited state, if you look at the potential energy surface, this is how it looks. Now, because there is a transfer of population of the electron cloud in the excited state, it won't be characterized by simple potential well, but rather a potential well which looks like this. Okay, there is small activation energy, and once this activation energy is obtained, then the electrons can be, the population can be either here or here, and this is, if this is the local excited state, this is the IC state, ICT is ICT, so Session state. Now this state can be tuned by tuning the molecular structure, by tuning the various solvent parameters. So all these things are possible, and looking at the potential energy surface is very interesting because these can be obtained by the Cornell intersection dynamics. In fact, I have shown you on one of the slides, we said we can look at the torsional motion of the molecules. That is what we can do here. Okay, so a lot of interesting aspects are there, I will not read it out. The point is that the ICT polarizes the molecule and leads to generation of non-zero dipole moment. So this non-zero dipole moment allows to makes this useful for various non-linear optical applications. Okay, so you can do various engineering part of it. Of course, I cannot do, chemist does. So they do the spacing. They change the functionalization of the functional molecules from the side chain its functionalities. They change the spacing length. They change the dopant of the molecule. Like if it's a porphyrin, they change the metal. So various aspects are possible to tune this property, and that's how you can pick up the same chromophore by using functionalization of the molecules. You can obtain various functionality. Okay.
So you're talking of this dipole moment, right, of the ICT state.
So
is it generally higher because the charge transfer, so people expect the dipole moment to be higher than the LE state.
Sorry, sir?
The charge, the dipole moment of the ICT state is generally higher than the LE state, right? Locally excited state.
Need not be. It can be high, it can be low. I'm just showing one cartoon. It can be anywhere. Because so if it is lower, then but the problem is that the issue is that this ICT state is now charged, because of which the potential energy is slightly lower. Typically, they are lower than the singlet state, and that is very sensitive to the surrounding solvent. So if you have more electromagnetic, more polar solvent, then it will be much lower. So that would keep on moving up and down. So that can be doing all this. The solitochromic bath shift will be there in these materials. Yeah. Okay. So one of the examples of how you can use this molecule is by Dyson solar cell, where the dye absorbs the light. Okay, it injects, once it goes to excited state, it injects the electron onto a titania. Okay, and this charge is lost to the titania, because of which the dye becomes positive nature. So one can follow how fast the dye becomes positive, and by following the dye the charges, how fast the charge is formed, you can actually track the injection dynamics of this charge, okay, of the electron. Now this is just for the students, how does it work is a dye, it absorbs the light, injects into the titania. Titania is a high band gap inorganic system, and there is a faster mobility of the electron. So once the electron is injected, it quickly goes to it percolates into the electrode. Now this dye is now positive, so it cannot absorb any more light. So it would try to extract electron from the surroundings. By virtue of the fast mobility of the electron in the titania, it cannot get the electron which it injected into the titania. So it will look for a surrounding, and that is obtained by this electrolyte. I just mentioned to you about Fe3+, and there is this redox kind of thing, 2+, 3+. One charge imbalance will be there, and that imbalance is what creates this redox reaction, and in that reaction the electron is now given to the dye. Now dye goes to the ground state, and another event of absorption happens. Now that's how this DSSC works. And importantly, the strength of ICT improves the electron transfer characteristics. The better, the higher efficiency. Okay, so structural aspects and relationship mainly affecting the energy of the frontier molecular properties are the very much essential for these optical properties. And various things are happening at different time scales, and we can follow these times. That's the idea of this figure. Now, look at the bulk heterojunction solar cell, what it is. It's a different kind of technology where you have a bicontinuous network of donor and acceptor. So this is the simple cartoon of it. You can have domain of donor, domain of acceptor, and they somehow get mixed and both are connected to the respective electrodes. Okay. So what happens is the donor, as it is donor, it absorbs the light and the exciton is generated. Exciton is a neutral particle and it just wanders around till it reaches the interface. Okay. Once it reaches the interface, it's called the exciton diffusion. It dissociates because at the interface the dielectric breakdown happens, because of which the electron hole pair gets the additional energy to move. So the dissociation happens. The donor injects the electron, so donor becomes positive and electron is in the negative charge, and they would quickly percolate through the respective channels and form the charge. Okay. So the main aspect of this usage is that the donor and LUMO, the donor and the acceptor should have energy levels which are given here, okay, which are as shown here. Donor should have a higher energy level compared to the LUMO from the acceptor, so that delta injection happens. So that's how it is chosen. Again, the structural aspects are important, and also we figure out that the small molecules have better opportunity to do more engineering, and that's the thing here. Okay. So as I said, our interest is to work with the porphyrin systems. I quickly present in this slide why it is interesting. So you have, this is a porphyrin chromophore. Okay, various numbers are there. Beta is given by meso is given. Okay, so this endpoints are meso positions 5, 10, 15, and 20. Okay, now there is a theory by Gautam orbital model which says that in the ground state, this HOMO levels have orbital density mostly on the porphyrin meso positions, and nitrogen atoms is the small electron. So this meso positions which I talk about it, 10, 20, 5, and 15, they have lot of electron cloud in the ground state in the HOMO level. So moment you functionalize them, then the various functionality starts increasing. Okay, this means the porphyrin functionalized at these meso positions would be expected to have so strong effect of the property. Okay, overall core. And similarly, as I mentioned to you, this ICT would also induce non-zero dipole movement, and this non-zero dipole movement would have a strong change in annular properties. Okay, so I'll initially present the work on this etc. dynamics of this two porphyrin systems. One is by my collaborator in Kuribabu. It's a porphyrin naphthalmide download acceptor system. Another one is from China, and these are the molecules which are used for organic solar cells. Okay, so first thing we do is simple steady state PL and absorption, because that is the first thing we do. Always you have to do absorption and emission to understand the material system. Okay, now we see that different molecules with various metal core. Okay, one non-metal, nickel, copper, zinc, and iron. Okay, Fe is 0, no metal. So nickel, copper, zinc. So each of this, by varying the metal, center metal of this molecule, the absorption is changed, also the emission is changed. Okay, similarly the time result absorption emission would also change. Now our interest is to look at the transient absorption studies. First thing we do is look at the solution part. Okay, so I would not get in detail of all the details of this work, rather I can just share this paper with you later. It's a last year paper. What we see is that we look at the solution pump probe and form a photophysical model, and this is the photophysical model which we do. It goes to a higher singlet state because we are pumping at 400, and once it goes to higher singlet state, it should relax by internal conversion to the singlet one, S1, but it cannot directly come to the lowest energy level of the singlet, so rather it relaxes to the vibrationally hot singlet 1, okay, which is called as S1 star, and it does the vibration relaxation in the excited state to come to the S1, and that's how one can do the rate level system. And after that, once it goes to singlet, it will do the intersystem crossing, get into triplets, or it may as well do fluorescence and emit fluorescence and come to the ground state. So once the population reaches to the singlet, it can go to triplet, it can give photon by radiative emission and come to the ground state, or it can also do non-radiative emission, non-radiative decay, which means it is not this, not this. For that, we need to use the quantum field of the emission. Okay, we do that. So all these things we take into consideration, we obtain the various rate constants, where the initial K12 is ranging from 375 femtoseconds to about around 300 to 400 femtoseconds. That is the quickest time scale you have. So internal conversion, so these molecules, once they go to the highest singlet, higher singlet, now S1 and more higher, they cannot survive there for long. Okay, so they cannot, they're really energetic that they cannot, they cannot stay in that conformer. Actually what happens is that energy level is, once it gets excited, the conformation changes. That's how the absorption happens, and now they cannot stay in that conformation, so they quickly relax to the first excited, which has slightly higher lifetime. So that part is called internal conversion. Okay, higher singlet. That's what Kasha rule says that, yeah. So that's the thing. Higher singlet doesn't happen. But there are molecules where Kasha is also failed, so I didn't say that, yeah. Okay. Yes. Now, these molecules are interesting because there was a paper by my collaborator in 2022 where they made self-assembled monolayer of the system and used it for the photocatalysis, green hydrogen. Now, hydrogen push is there, a lot of money is there, people are doing this. So, our interest is very, very humble. We want to look at the electron injection. And that's what we wanted to do with our POMPROB study. Okay. Now, how do you do that? This would be not in solution but in thin film form. So, we make a thin film of it, make a film of this dye on titania and look at the injection. But earlier if you look at it, we just looked the dye in solution, which is not the true reference for this material. So, in order to compare the injection, we need to have a reference where the dye is sitting on a oxide system with similar conformations, with similar kind of corrugation or whatever, but should not inject. For that, we choose the zirconia, ZrO2 zirconia as the reference. So dye on zirconia, dye on titania, and zirconia doesn't inject, titania it injects, and that's how you look at the injection dynamics. So this is the absorption and emission on titania film, okay, and this is how the PL looks. Now the interesting part about this injection studies is, once the material is once the molecule is excited state, population is excited state, right? Now, if it relaxes, it would give away its photons, and emission is what it is. But if it loses its electrons via electron transfer to an acceptor, the population in the excited state is reduced. Okay, now reduced population will emit less light, and that's how, by looking at the steady state emission of the molecule on acceptor system, you can quickly see whether there is an electron injection or not. And that's the point which we see here. In the case of metal free, there is no much electron injection, but in the case of zinc, the PL decays very much. It is 95% quenching is happening. And that's the first proof that there is electron injection. Now we want to look at the efficiency of it. Okay. So why it is happening? We do the pump probe here. I will not again get into the nitty-gritties of this. All we do is, this is the pump probe of film on zirconia. This is the pump probe of film on titania. Okay. Sorry. Z are all zirconia and titania or Ti is titania, top and down. So we look at where it is changing. Okay, first thing we can see is that this part is completely changed. Okay, and this part is quickly quenched. Here in the case of in case of Fa, nothing is happening. So we look at the various individual parts of the spectrum and we do fitting. So now we cannot use the fitting we did for the solution. So we do the fitting for the film on zirconia to look at the excited state properties. Same thing we repeat, but in film data. Okay, and we obtain the rate constants. Again, it changes from 306 to 295 initial time conversions, and it all changes. Everything is different. The same time rate constants are calculated, but they will be different numbers because now it is in film form. Now the interesting part, what happens on titania? Okay, now what happens on titania is very interesting because the moment you put the titania, where do we see the electron is injecting from? Okay, so that is the point which we addressed in 2020 paper. I told you, multi-step injection. So here we follow the same thing. We say that the injection is happening from all the excited states. It's a modeling, right? No one can know where is the modeling happening, where is the injection happening. But from modeling perspective, this is Sn. You can say Sn2 titania. Why not? Hot singlet titania. Why not? and singlet to titania. So one may ask what happens in the middle. For modeling we don't use it, but it can happen. All we do is now we do the same fitting for this kind of system and we obtain the rate constant. Now interesting part here is that the fastest decay happens in 250 femtoseconds, which is shorter than that when it is at the film form on titania. Okay, so now the initial decay rate is happening faster than the internal conversion process. So there is a competition between K12 and this guy is winning out. So this is a proof that the injection happens very fast and it is happening from the much higher singlet state. Okay, so and also one can track the population change from metal free it is 35%, and with zirconia, with zinc, where you have the maximum PL quenching, the population transfer is 70%, 72%. So majority of the population is now decaying within the first 300 femtoseconds into the titania. So this proves that there is hot electron injection, and also when you look at the recombination rates, this is the T50, we see that the recombination rate is way much higher in microseconds. So injection happens, charges are formed, the charges are not recombining till microseconds, which means the charges which are there in the titania are having sufficient time for them to really get extracted to the electrodes. And that's how one can say that this kind of metal system would work very good for the, any of these energy applications, be it photocatalysis or dye sensor solar cell. So that's how one can look at it. Now second part is, I'll quickly, now that you know the story, the same thing story, just that here we have 3 molecules. Interesting part about these molecules is that one gives 8%, another gives 8.5% efficiency, and third one gives you 11.5% efficiency. So what are these molecules? Okay, injection is with respect to the PCBM. Okay, now porphyrin molecule, which is A pi D pi A. This is the kind of molecule system we have. Okay, I'm not a chemist, so I will not talk about it much, but rather I would show you, draw your attention to this central moiety, 1 porphyrin, and efficiency of 8.8%. Then we have another molecule where this center moiety is multiplied into 2, so it's made dimer. So one is monomer, one is a dimer. So we have 2 porphyrin cores separated by 1 pi spacer, and that gives you 8.45% efficiency. So one can think that if I have 2 porphyrin molecules together, then I should have more information, more efficiency, but no, that's what it shows. Now they found that if they replace this simple pi spacer to another molecule, which is an acceptor system, then you have, this is an acceptor, pi, donor, acceptor, donor, acceptor. Okay, so A pi D, A D pi A. So this is the kind of engineering they have done, and that has the same system, the same porphyrin core, zinc porphyrin core, gives you 11.25%. So it is about increased by 2% efficiency. So why? That's the question they asked us in the BRICS project. So we see that the moment you do this kind of where is it? In kind of this 2, 3 DPA and other things, the energies are changing, which is what expected. That's why you do the DFT calculation. Now the efficiency should go because the PCBM has a lower energy level, which matches the criteria of the electron injection. So now we look at the PL quenching. Again, PL quenching is maximum for the for this 2 core with center acceptor. Okay, so there is efficient charge transfer in the excited state for that third system. Now, what is the molecular design impact? It was found that, again, DFT calculation, my collaborator, he found that there is higher D dipole moment for the third case for this particular molecule, and expected to have better interchannel transfer, ICT. Okay, that's the idea of the better ICT. Okay, so this is the HOMO-LUMO picture. That's why I said, right, electron cloud shifts in the LUMO compared to HOMO. Okay, and we do pump probe on the film, simple porphyrin film on glass, and porphyrin with blend, PCBM blend, and look at the PL change, absorption, transient absorption changes. I just highlighted 2 areas in the visible and the IR, NIR. So it is from 402 all the way up to 1350. The entire visible and the near infrared probe is done. Of course, we cannot access the 800 because there is a strong 800 pump in the continuum. Okay, now to look at the difference, we look at the delta dA. So this is already D delta A by A. So we subtract this with this. Okay, so we do DDA, and we see which is the difference of this with the blend and the film, which is showing up. And we see that that's showing up around 950 nanometers, which is the charge species of this PCBM, and tracking that species gives us the injection about the efficiency. And we find that the instantaneous formation of charge transfer state happens, and that happens within 200 femtoseconds. We cannot probe below 200 because of the issue with the instrument response, but rather, looking at the ultra-fast formation at 740 kinetics, we see there is instant formation of CT state, okay? And looking at the 10630, as I said, there's a charge species of the PCBM kinetics. This dissociation happens in 250 femtoseconds, okay? Now, I'm talking about very, very fast rates where the dissociation happens. Why we don't want to, just to ask students why you want the dissociation to be very fast? Because there's always a competition between the excited state relaxing to the ground state, okay? That's the natural decay. We want to win over that natural process in order to extract maximum population from the excited state. Now that is the idea of it, and looking at the long-term recombination, which I didn't show here, it goes beyond 3.5 nanoseconds. Okay, so this is the global analysis of the spectral window in the visible, okay? As I said, you get the SATs, the basis sets of spectrum and time. This is how the spectrum and time looks. 1, 2, 3, 4. Four elements were found, 4 spectrum and 4 times. And the other ones is a linear combination of these two, where you can generate the entire story of the pump probe in the visible and also in this NIR separate, okay? So we had to do separately because these are two different experiments, we can't big them together. Right, so overall, long-term disease nanosecond flash flow is also done to look at the, recombination ratio. So recombination says that the blend has non-geminate recombination. Just to say what is geminate, non-geminate. Once as you say, there is a electron hole pair formed at the injection, okay, as soon as the injection happens, there is still Coulombic attraction between the electron and the hole pair, okay, even though the electron is in the donor. When they combine, that's called geminate. But if you give sufficient time, little bit more than that, they get dissociated and they travel. So the electrons travel in the donor, in the acceptor, and holes travel in the donor. Now, during their journey towards the electrode, they may always encounter another opposite charge and they recombine. So that is called non-geminate recombination. So it is also important to worry about what happens in the journey. That's the charge transport part. So this particular system shows that the non-geminate recombination is very poor. And that's how we have a situation where you have slow recombination rate and long-lived charge band, because of which you have the more efficiency. And that's how we proved for the third case why the efficiency is higher than that of first system, which is 8% and 11%. Okay, so this is right now under review. So anyway, it is we are submitting the revised version tomorrow. So summarize the two parts which I said. We explained you about the DSSC part of it, the photocatalysis, the injection is studied, and I also explained you about the injection into the BCBM. So I explained you two different types, DSSC part, again energy, photocatalysis or licensed solar cell, or OPV plant. Okay, so that stops our discussion on this ultra-fast carrier dynamics. Now I'll use next few minutes to talk about the modulation. And this modulation is, for a very, very strange reason, our femtosecond laser failed. Okay, so there is the guy who got the exam results with the previous one, wrote a paper, and the one who is following that work, who is assisting his work, could not proceed with the work because laser is not there. So he was frustrated. And this work came out as a frustration of him, okay? And this is two publications, I'll just come to it. Very nice, because he was frustrated, he did not know what to do, he figured out what to do. So what is it? We picked up these molecules again. He has a porphyrin and phthalocyanine from the same group. And this phthalocyanine, this porphyrin has a paper, 2023, and this phthalocyanine is published in another 2023 paper. Now both of these molecules, we understand the femtosecond pump probe as well as the nonlinear nonlinear optical properties. We know about all these things. Now, these are all femtosecond, ultra fast. Now what to do with this when the laser is down? So the student said, okay, let me use my CW laser. So we have two Chinese lasers, one in 440, other one is 532, 30,000 rupees laser. And we started looking at the how the transmission happens. Now that is the beauty about this CW interaction with the laser, with the material, where you expect thermal nonlinearity. And the effect of thermal nonlinearity is this optical phase modulation. What is it? Now, spatial self-phase modulation is a coherent light matter interaction in which the modulation in the optical phase of the light results in the change in the nonlinear refractive index. Okay, it is expected. There is always a change, which is what gives you the phase change, because of which the nonlinear refractive index, that's expected from NLO. Now, the point which we see is that because of this sudden change, and here you have the effect of non-resonant nonlinear refractive index plus the thermal nonlinearity. So all these things will contribute to it for giving you a nice diffraction ring which looks like this. Not diffraction, it's called spatial self-phase modulation. Okay. So based on SSPM concept, cross-phase modulation in which two light beams cross each other at the nonlinear sample to modulate off phase is also studied. Okay. So you can have one beam going to give you one spatial self-phase modulation. You can put two different colors and you can see the effect of this and that together. So that's how we can look at these studies. Okay. A lot of interesting applications are there for this. And what is this? Why you have this kind of self-phase modulation? Okay. Spatial self-phase modulation. So that is the laser and is a sample and this is what it is. So what happens is the mechanism here. So let's say this is the Gaussian beam profile of the CW light, and as it interacts with the sample, okay, there is a nonlinear phase shift. If psi NL is the nonlinear phase shift given by the you integrate from 0 to del effective of intensity and the nonlinear refractive index in the range from 0 to infinity, you see there is a change. The change in the phase, okay, matches for two different radial distances, okay, basically because it is symmetric, okay, because of which you have a situation where, oh, I'm pressing the wrong thing, sorry. We have a situation there, this phase is changing and that would lead to the formation of the interference pattern because the change in the phase is the same. Okay, so the bright and dark thing can be determined using this phase change, and what you see is this kind of interference fringe which show up as a nice diffraction pattern. It's a circular too. Okay, that's how it is. Huh?
Are these co-ed based measurements or they're
It's clear, simple solution. Of course, we have done it in the film. I'll show you that data also. So now this variation is now intensity dependent because nonlinear. So higher the intensity, higher would be the effect, and that's how we see. As you change the intensity, the ring number increases as well as the size increases. There is one more cute thing. You see this kind is slightly compressed compared to the doped one, and that is because of the convection current. Okay, so one can look at the variation of the ring number to the intensity, find the slope and use this slope information dn by di, okay, to get the nonlinear refractive index and the chi3. Now this n2 is combination of thermal nonlinearity and the non-resonant n2. Okay, both can happen. It can be resonant or non-resonant, but n2 we just keep it as effective n2. That's why it is. I am saying it. It is the combination of both. In fact, we have calculated, and the numbers are of the order of 10 power minus 5, which is almost the same you get with the thermal nonlinearity. So that's why we say both are contributing to it. Okay, so with porphyrin molecules we start doing it. Different colors. This is with blue laser, and this is a red laser. Okay, blue 440, red is 630. We should not talk about color now. Now again, one can get the N2 values of it from both these colors. Now using this material, another material for phthalocyanins, this is what we published recently, we again obtain the same numbers. So all we do is that just pick up the molecule and look at the N2 part. That is the standard part of it, so that we are happy with it. However, we want to go further and see how the system can be used for the application part. That's the point which is we are talking about it.
Santosh? So you will also have molecules moving about it. This translation and other.
Sorry?
Brownian motion. Molecules moving about in the solution.
Brownian motion.
Yeah.
I'm coming to that. The effect is interesting. I'll come to it. I hope I have it here. Next slide. Yeah, it is there. Yeah, the Brownian motion. Yeah. So the numbers are obtained from the simple calculations. Now, how this change is happening? As I said, I just play it here. This is how it looks. Can I not go it? It's not playing. It's okay, fine. So this would show that. No, it's not happening. Huh? Okay. Yeah. So you see, once it forms, it blooms and goes down. Again, I'll play. So initially when you see, it is really symmetric and then it comes down. Okay, why? That's the idea of the, I can just change it back. This one. Yeah, it's okay. Yeah. So we see that initially you have the symmetric, but it goes down. Why is it so? Because that's the convection current. As you say, it's a heat, right? Thermal. So there is a convection current and also molecules moving up and down. And that's the point which we see as you change, as we plot with respect to time, it is moving from a symmetric to asymmetric. Okay, in 0 to 1.29 seconds. And that's same for all the colors. Okay. So I'll come to it. Why it is so? Because of the convention, it gets bubbles are formed. Okay, bubbles are formed because of thermal nonlinearity. Bubbles are formed and they start going up. As they go up, they start replacing the molecules on the top, and the molecule starts getting compressed down because bubbles go up. Because of which, even though the beam is Gaussian, it just that there's lot more molecules which the center part is seeing now, and less molecules at the periphery. Because of which the donor, let's say this is a circular spot, you see in this bottom half nothing is happening. In the top part, the molecules are now bringing down because of the bubbles, because of which a lot of molecules are now being pushed down and they are interacting with the higher intense portion of the beam. Okay, because of which you see there is no interference pattern what you see there, and that's what is now built down. This is also there is a nice model called Wing chime model which can explain this. Okay, now applications based on this. One, you have a cross-phase modulation, just like how you have one beam giving you this pattern, you can also have other beam. Now, one can change the intensity of one pattern and see how it is moved to the other. This is what gives us the simplest example of at OR gate. Okay, when both intensities are low, you don't see anything. When this blue intensity is high and red intensity is low, the output has transfer of energy, because of which you see high. When blue is low, red is high intensity, basically increase the intensity. You see both are there and both are high, it goes. Of course, this is very nice way of talking about it. You cannot play any other, you cannot get any other OR gate, any other gate, because if there is intensity, it would show up. You cannot have a situation where it is eaten up. So we are looking at how to solve that issue. Okay. Now that is the idea of all the colors. We get it. Okay. Now this cross-phase modulation now can be used for device application. So what we did, we picked up one ring part of it and collimated into a detector. As you see here, this is the example. This is how you just get the detector and see now the effect of variation of this input beam with the variation of the intensity or the power or the of the detector output. Okay, so this is the detector, and so as you modulate 532, the ring also changes. And now this is the one for say 533 and 633. Here you have a situation where the pump of 633 and probe of 532. So you vary the pump 633 and see how the probe 533 is changing. Okay, and you see the same variation which you impart in the pump is now being seen in the other side of it. Now that's how you can transfer the energy information from one beam to other beam, and that's how one can talk about the optical modulation. Okay, now this is the idea of the mono wavelength region and two wavelength region. Now in this slide I'm displaying what happens when you use a thin film and not a solution. Because in the solution you see there is a dip in the top, right? Here you see it is now symmetric because there is no convection planet to show it. So just to prove that this effect is mainly because of the solution and everything remains as it is.
Santosh, in your solution measurements, so you have bubble formation, right?
Yes.
So bubble formation also the refractive index is changing. That I don't know what effect that.
Sorry.
Bubbles.
No, you don't see this is so. Let me correct myself. I don't see a real air bubble coming up. Okay, the intensity is still low. So this is like slightly above that, below the threshold where you actually see this burning. So there is no evaporation, there is no burning. So there is no variation of this hot air coming up. It's just that sufficient energy where you see this happening, and one can assume that that is because of the small nanobubbles. If you increase more, then you start seeing that molecules burning also. So we are not getting into that.
What is the intensities you are talking of?
Huh?
What is the Intensities you are talking of.
Intensities, I shared, hold on.
And what is the spot size?
It is about 3-4 watt. I think I had it somewhere earlier. I'm sorry. Watt per centimeter, but I'm seeing the number. It's about watt per centimeter, not much. Okay, it's somewhere there. It is there. I moved a lot of things here. About 3-4 watt per centimeter, sir. Up to 11 maybe. So this is the time image of it. Okay. So now you can play with this. Now that we know it is there, you can give one signal to it and see the other signal coming up. That's how you can get the information transfer. And what we did is we have given encoded the IATH in ASCII code, and we gave to one light. We just gave function in it. So you vary one and you see the other one is also mimicking the same. So that's how we demonstrated this optical signal. Okay. Then comes the idea of photonic diode. Now this is little interesting because the hybrid structure of two different band gap placed close to each other in SSPM can be used as photonic diode for non-reciprocal light propagation. What it means is that if you have one system which is highly nonlinear, absorbing, and other system, and light goes through it, by virtue of this absorption and nonlinearity, the effect shows up. Okay, you see that kind of spatial self-influence modulation. On the other hand, if I reverse it, which is the case happens here, I have the porphyrin, which is absorbing and having good nonlinearity, and CS2Ag ion 6, that is the halide double perovskite, which doesn't have absorption at 532. It is high band gap but highly nonlinear. Okay, so now we see that if I put my if I send the light through this porphyrin and CS2Ag3, I see this pattern. On the other hand, the reverse, I put the CS2Ag6, which is the high band gap system, followed by the porphyrin. I don't see the nonlinear effect. So one can dub it as a simple idea of optical photonic diode, and that's how we can look at the variation of this ring number by doing all the experiments we did. When we reverse it, we don't see any output. On the other hand, you can actually see the rings. Okay, so few things I have explained you, few things I said I cannot do. For that, for example, we cannot go anything beyond OR gate. Of course, when there is material, when the intensity NLO shows up. So that is how we have showed as OR gate. But anything else, one needs to go a little deeper. So we thought a polarized light dependent study is important, which is what is the ongoing work. People are doing it. Okay, so this is the last slide. So in this talk, I have explained you our results on excited state dynamics and all optical modulation of non-organic molecules. So I explained you example of hot carrier injection in metallated porphyrin complex adsorbed on titania, charge transfer state formation and recombination in porphyrin PCBM system. We also showed you coherent right matter interaction for optical switching and logic gate and photonic diode application. So few things are published. The last two are still in the review stage, so it should come up. And with this, I thank you all for your attendance.
Nice talk, Santosh. Yeah, so this you talked about hot carrier injection, right?
Mm-hmm.
So that depends on your exciting the molecule, and then the electron gets injected into your whatever is your donor, or in another case zinc or zirconia or something you use.
Mm-hmm.
So how do you model this? Can you calculate those rates?
Yes, that's what I showed you that number.
Experiment. I mean, theoretically, can you calculate them?
Theoretically, there are groups who are doing ab initio calculation. They are able to do that. It is possible.
So
it is possible. It's computationally expensive. Because now for titania you need to have more. It's like wider net of titania. So it's computationally expensive to have that kind of thing. So people have done it. They have taken 44 or 48 titania systems, and they left one molecule and let it stabilize one pond, and they have done it. So that's how people have done it. It is done. It is possible. Yeah.
So these are comparable to the experiments.
Sorry?
The values which you obtain.
So
you can they mimic the experiments.
Yes. So look, there are slight. Let me clarify myself. So the hot electron injection is understood. Is is now proved theoretically, but looking at experimental proof of multi-step was not shown till now, and that's what we have shown. So that is the main contribution from our work. Because generally what everyone thinks is once it goes to an excited state, it relaxes down to a singlet and injects. Because once it is in higher singlet, no one can think that it can do anything other than relaxing to the lower singlet.
Generally, those time scales are like, those are faster. Man.
Yes. So, in fact, the clue comes in the way we observed the formation of the charge band. Okay, so how did we get it? It's not that we computed to look at it. So, when we see the charge band formation, so the way we do it is, I can digress a bit. You take the molecule and do spectroelectrochemistry. So, you physically photodope, chemically dope with charges and see the absorption. So, you see the absorption. So, if you start chemically make it positive, then you see where the absorption is happening. So, the place where it is absorbing, once it is chemically doped, we see that signature in the absorption here, photon-induced absorption. So, this guy moves there, and that's where it starts. So, we see when is that forming, and that is happening in 250 femtoseconds.
From the, like, if it is basically a vibronic overlap, right? How well your system couples to the higher vibrational levels?
Yes, it's a Marcus theory.
Yeah.
It's a Marcus theory.
So
It's a simple Marcus theory where that's how the rust is, the Fe2 plus Fe3, the rust is proved that way, right? Marcus theory. The same theory is used here, where the donor acceptor and they have the potential well overlap, and that small activation energy it requires to inject. That small activation energy is obtained by the higher, the difference between the LUMO of the donor and conduction band of the titania. So that's where the more it is, the more is the injection. Yeah.
Thank you for your insightful talk, sir. For the want of time, we'll take any further questions offline. Thank you very much.
Yeah. Please approach me for the papers. Yeah. Thank you.
Thank you, Professor Santosh, for sharing your expertise in the field and providing us with your insights. I now request Professor R. Gauri Shankar to give away our token of gratitude to Professor Santosh. Thank you, sir. Moving forward, I deem it my privilege to introduce to you all the next speaker for the day, Dr. Manish Kumar, who will be joining us online. Dr. Manish Kumar, an esteemed assistant professor at IIT Delhi, is a versatile researcher with a strong background in physics and optics. He completed his BSc and MSc in physics with photonics specialization at Sri Sathya Sai Institute of Higher Learning before pursuing a Master of Technology in Applied Optics at IIT Delhi. Dr. Kumar obtained his Ph.D. from IIT Delhi and further enriched his expertise through postdoctoral research at the University of Michigan and Northwestern University in the United States, focusing on imaging through scattering media and advanced light sheet microscopy techniques for neuronal imaging. As the leader of the Bioimaging and Optical Systems BIOS Research Laboratory at SENSE, IIT Delhi, Dr. Kumar's work revolves around inventing and developing advanced microscopy systems, optical flow visualization techniques, and computational approaches to enhance imaging capabilities. His research contributions span across physics, electrical engineering and computer science, and neurobiology, showcasing his multidisciplinary approach to optics-related challenges. Dr. Kumar has been recognized with several awards and honors, including the Young Faculty Incentive Fellowship from IIT Delhi, travel awards for prestigious conferences like Sculpted Light in the Brain at the Royal Society in London and SPIE Photonics West, as well as fellowships from CSIR and MHRD by the Government of India. His upcoming talk on remote focusing light sheet microscopy promises to shed light on the innovative field of remote focusing imaging and its application in light sheet fluorescence microscopy. Dr. Manish's expertise and contribution to the field make him a valuable addition to today's discussion. Let us extend a warm welcome to Dr. Manish Kumar as he shares his insights with us. Dr. Manish Kumar.
Yeah, Saram everyone. So I just need one confirmation before I start. Can you see my screen properly and can you hear me properly? If someone could confirm it.
Yes, sir. Thank you. We can hear you. We can see your
Okay,
presentation.
sure. So I'll get started. Okay. All right. Thank you for inviting me. It's a very different occasion for me. The very place where I have studied, giving an invited talk. So it puts a different kind of pressure on me. So I hope I do the justice. Uh, the work which I'm going to present today is mostly done by me when I was a postdoctoral research scholar at Northwestern University in Department of Neurobiology. So the work is going to cover most of the aspects are to do with light sheet microscopy. And probably this term may be somewhat new to you. And even the first part of my title, remote focusing, may be somewhat new. So let me just try to introduce all these concepts in very simple way, probably. If required, anyone can interrupt me in between and ask questions. If it is audible, I will stop and try to clarify. Okay. So let's start with something very simple. Microscopy, it depends on a microscope objective. That's the most critical part of any microscopy setup, right? And for a given microscope objective, there is this special plane which is called working distance, right? So if you ever use a microscope, you will see that only a sample plane which lies at the working distance is in focus, right? So that is the first aspect which you need to keep in mind while going further through this talk. The second aspect, which is not that critical, but I just wanted to mention that most of the microscope objectives are infinity corrected. So what it means is that you have a tube lens, and beyond the tube lens there is a camera. So the distance between tube lens and microscope objective, this does not matter so much. This is not so critical. Okay, so working distance is fixed, but the infinity corrected objective means that this distance is flexible. Okay, so if everyone gets this, let's ask the next question. How do we do a 3D imaging with a microscope? So if you ever have to do a 3D imaging, the most common approach is you put your sample, which is a thick sample, and therefore you can see only one single plane at a time. And then you need to scan your sample along the axial direction, which normally here we may call Z-axis. So you take a translation stage, you mount your sample on there, and then you move it either manually or automatically. There may be different approaches of doing it, but everything involves either moving the sample, or in some cases, you could also move the microscope objective because this distance, as I mentioned, is infinity corrected, right? So this distance does not matter so much. You can move the objective up, down, or sample up, down, and therefore do a 3D imaging by capturing multiple images. So axial or Z movement, if you do it with stepper motor, they are slow. Piezo stages are fast, but there are some drawbacks. In either of these approach, if this sample happens to be a living sample, then you will end up inducing some vibrations. If it is a soft sample, then it may undergo some amount of shear, and therefore the volume actually you will reconstruct will not be the actual representation of the real sample, right? So for such sample which are living or soft, this approach is not that good. Okay, so that leads us to a question: is it possible to perform a 3D imaging without moving the sample or even the microscope objective? Okay, so can we do this focusing remotely? So on the this image is showing a typical microscope setup in which you have a fixed working distance and we are scanning the sample. But what we want is we don't have to move the sample, but we can move this working distance somehow. So the working distance itself can be moved. Okay, and that is we are calling it as remote scan. Okay. So this approach has been introduced long ago from today's perspective. Back in 2007, this approach came up, an optical technique for remote focusing. I'll briefly go through it, very briefly, not bothering about the mathematics involved, but it's basically a problem of optical system design, and designers sort of knew this long ago, but it's just that no one realized how this can be used for a real application, So a perfect imaging system in optical system design is one in which whatever is the angle of incidence, the imaging system does not change it in any way. It kind of just mirrors it. So if the gamma 1 is the angle here and gamma 2 is equal to gamma 1, if somehow an imaging system is formed in such a way, then this will have least amount of aberrations possible. Okay, the disadvantage of this system is that it's 1:1. There is no magnification involved. There is no demagnification involved. It's just 1:1. And all this is based on the assumption that N1, the refractive index on the object side, and N2, the refractive index on the image side, are same. If they are not equal, then here is a simple formula for magnification. If you can form an imaging system with this kind of magnification, then it will satisfy this condition where any angle, any ray which is subtending some angle with optical axis, when exiting the system, it will subtend exactly same angle. And when this happens, you have least amount of optical aberrations. And that means whether your sample is at this red dot here, or at green dot here, or at gray dot here, this will be perfectly imaged onto the imaging side. This is a perfect 3D imaging system. Okay. So, okay, remote focusing microscopy makes use of this. There is one drawback which we discussed here, that the magnification is unity. So how do you magnify? How do you get microscopy in the picture? You put one more microscope. So here is a simple system which can do 1:1 magnification. So you have one microscope objective, one tube lens, and typically here is where you put your camera in a normal microscope. But in this remote focusing setup, you are not putting a camera here, but you are again continuing with the same system in a reverse manner. So you have second tube lens and a second microscope objective, which are exact replica of what is on the left side. And because of this symmetry, whatever sample is placed here in the volume, that gets reimaged over here. Okay. And it has been shown by the same researchers that in this particular configuration, if you actually happen to get the point spread function, you can see that on the left is conventional way of imaging, in which point spread function actually elongates as you go farther away from the working distance, and therefore the image quality deteriorates. But if you do it in the remote focusing manner, then the point spread function remains consistent for a very long distance along the z-axis. Okay, so you are effectively able to image the whole volume which is in front of microscope objective. So now this is what is happening. You have, for simplicity, I have omitted the tube lens in between. So if you have two microscope objective back to back, then plane 1 gets reimaged as plane 1. Here plane 2, plane 2, plane 3, plane 3. Okay, so that is fine. But let's see. Okay, here is one more extension of this. So if you have a sample which is in 3D, this whole sample gets reimaged here in the image volume. Now let's ask another question. What if we are not focusing on these planes which are perpendicular to the optical axis, but let's imagine a plane which is oblique, which is tilted at certain angle. So what will happen to this particular plane? So in the same scenario, what will end up happening is that you can reimage even that tilted plane. Okay, And that is something which adds another dimensionality to this whole microscopy field. You'll quickly realize why so. So before we actually see the power of this particular realization, we are going to focus a little bit on to another concept, which is called light sheet microscopy. And we will see this realization here in the last slide actually leads to something called single objective light sheet microscopy. Okay, so here is very basic light sheet microscopy setup. I'm sure that all of the students here know about Gaussian optics. It's very simple Gaussian focus. You know that if you focus a Gaussian beam, it does not go to a sharp focus as we usually imagine, but it comes to a very the beam waste becomes minimum and then it slowly spreads, right? And here, right in the center here around, you have Rayleigh range. And within that range, you can assume that the thickness of beam is almost consistent, almost constant. And instead of doing a Gaussian focus, now imagine if you took a cylindrical lens to focus a Gaussian beam. What will happen is that it will undergo this kind of focusing only in one direction, but in other direction, it will be like a expanded beam. And therefore that in this particular region from side will look the same, but from top, it will look like uniform sheet. Okay, so it's basically forming a very thin sheet of light. And that is critical for light sheet microscopy. You just create this thin sheet of light and place your sample right here. Now your sample should be a fluorescent sample. That's the basic light sheet microscopy is always kind of assumed to be based on fluorescence. That's how every biologist uses it. So if your sample is fluorescing, it will fluoresce only in this particular plane, right? And now you know exactly if you have a particular plane which is emitting your emitting fluorescence, you can easily image that by an orthogonal configuration of microscope. So you basically have one microscope which consists of microscope objective, tube lens and camera to magnify whatever is optically sectioned here, right here. So you have one microscope objective which creates this thin sheet of light and another microscope objective combined with a tube lens and camera to magnify and image that, right? And that way you are able to create this optically sectioned image of a 3D sample. It could be a living sample as well. That is what has made light sheet microscopy so popular. Now, recombining the concept from previous slide, what if we had ability to image this oblique plane as we saw in the context of remote focusing? You see, light sheet microscopy comes with two objectives surrounding your sample, and therefore it is highly constrained. You don't have lots of freedom to place your sample. If you have very large samples, they cannot be imaged here at all because they will have to fit within the working distance of these two objectives. That constraint can be removed once you are able to image it like an oblique plane, right? And that you have to, if you have to get a magnified view, as we had kind of understood from previous slides, you can put a third microscope objective right here and then image your plane of interest, put a tube lens here and camera here and get a magnified view as typical with the microscopes. So that is fine, but we are still talking about everything in terms of just imaging a single plane, but biological samples, as we know, are not a single plane. They are three-dimensional. So it's fine that we can do a light sheet of a single plane in this configuration and remove the constraint of having two microscope objectives. But how can we extend it for 3D scanning? Okay. So that problem was solved by Dunsby back in 2008 in this very nice paper. The concept I will try to walk through briefly here. So we take a laser beam and put it at an offset position and put it through a microscope objective. So once you have this offset, it is not co-aligned with the optical axis. So as it comes out of microscope objective, it will create a light sheet which is oblique. Okay. Then we put inverted microscope as we have been discussing here. So that will re-image this volume right here, and we'll get this same oblique plane re-imaged over here, right? And then we put third microscope. So okay, we are getting a static light sheet here, and we are able to re-image over here, which is further getting magnified and getting imaged onto our camera. Okay, so all that sounds good, but how is the scanning? So remote scanning actually can be done by now shifting this microscope objective back and forth. So L6, what you see here, if it is scanned with a piezo stage in this manner, that will effectively lead to the light sheet here in front of sample being scanned as shown in this animation below. Okay, so you don't have to move the sample. You don't have to move the microscope objective kept right next to the sample. You are moving a microscope objective which is kept remotely and still able to scan it, and no other part in this whole configuration has to move. You can get onto your camera the planes in various shifted manner and then reconstruct the whole 3D volume which is right in front of the objective. So that makes this whole setup so versatile. There is only one moving element, and without disturbing or inducing any vibration in your sample, you are able to acquire in a rapid way a 3D imaging. Okay. But it's again based on this microscope objective being moved on a piezo, and piezo stages are still not very fast. So we are talking now, we are become kind of greedy. Nothing is fast. We need to always be faster and faster. So can we make it really fast? Okay. So what is fast in physics? Obviously, I'm sure most of you know, galvo scanners are really fast. I have been very nominal in giving kilohertz. They are known to go up to megahertz, a few megahertz. Oscillation frequency is not so difficult for galvo scanners, and they are widely used for applications which are normally laser scanning microscopy, in which a single point is scanned in XY direction in raster manner, and you can do so many kind of things with this kind of scanning, not only for imaging, even for some kind of microfabrication, some kind of so many applications rely on galvo scanners and just doing this kind of scanning in X and Y direction. But then comes the problem, like, is it possible to use galvo scanners and somehow do things with what we were discussing in previous slide and make the 3D scanning with light sheet very fast? So this is what exactly I worked on. This is exactly where my work began when I was at Northwestern University. What I realized was that if you have this particular arrangement in which your galvo scanner rotation axis, so the axis along which it is rotating, if that is exactly at the back focal plane, and principal axis, if that matches exactly at these two cross sections of a given lens. Here I have shown microscope objective for obvious reason, but it could be any lens. If you have this kind of configuration and you put a laser beam which strikes the galvo scanner mirror and goes towards the lens, if you do it, it will create an oblique beam, obviously because of this offset, because this incident beam is not along the optical axis but slightly offset, it will create an oblique beam, oblique light sheet. But at the same time, now if you rotate this galvo scanner, you oscillate it, this is going to sweep this oblique beam along the lateral direction. Okay, So earlier we were focusing a point in, if I go here, in these applications, galvo scanner is just intended to focus a sharp point. In our application, I am extending it to for an oblique light sheet and same kind of lateral scan. Okay, now you can pretty much guess where it is going from here. I have also provided a proof, a very simple mathematical proof and a very simple experimental setup to showcase that this indeed happens if you match that condition of perfect placement of galvo scanner with respect to microscope objective, you can get this oblique beam scanned in the lateral direction without any change in the tilt angle of this beam. And that is critical, although I'm not going into that details, but if you happen to not do this and the tilt of this beam was changing and you kind of did the microscopy with that, you will end up again with a distorted view, which will be very, very computationally heavy to correct. Okay, so 3D scanning will not be perfect if this tilt angle was changing. Okay. So this is again a schematic showing a different light ray scan when the galvo scanner is rotating around, and then we can make it into a microscope. So a microscope objective has this back focal plane normally inside the objective housing, not outside. So in order to access it, you need two additional lenses, and then galvo scanner can be placed in such a way that the rotation axis of galvo scanner is right conjugated to this back focal plane of the microscope objective. And beyond that is a very simple setup as shown here. Don't get intimidated by how big or how many things are there. We can basically split it up. It's a very simple microscope objective. And then there are two lenses, as I mentioned, to conjugate the back focal plane right onto galvo scanner rotation axis. And then you need to redo the setup in inverted direction. So there is again one lens, two lens, and microscope objective. And this space becomes conjugate of the sample space. And the magnification is 1:1, right? So you are basically taking this volume and remotely putting it over there. And then you have one more microscope right here, which consists of a microscope objective, tube lens, and a camera. Okay. Now the advantage is as you control your galvo scanner, you are going to sweep the light sheet in lateral direction. And we are going to acquire whatever is here at very, very fast rate. Now we can control galvo scanner rotation angle and sync it with the camera firing rate. And by doing that, we are able to acquire multiple images at a given time. Very, very fast succession. Okay. I will straight away jump now, having described the concept, I will straight away show some random data set, what kind of data we can get out of this. So here is a Taiwan GFP expressing mouse brain section, and this is not cleared. This is a hippocampal region of the brain of a mouse. And you can see these neurons, the bulb-like structures are neuron. Okay. And this was on the first version of the microscope which I built. Acquiring this whole segment, this whole hippocampal region took around half a minute. Just for comparison, if one had to do this on a confocal microscope, it takes around 1.5 hours. So hours become minute or less than that. Okay. And that is not sufficient. Here is a simple scan of very, very large section of this mouse brain. So here on the top, on the left side, you see the top view of the section, and on the right side, actually you see what is actually captured on camera. So the top region is actually the surface of any slide. Okay. And you can see some irregular pattern because none of the slides, in spite of cutting it into nice sections is perfectly smooth. It's a biological sample and it will have its own variation, right? So you see on the top the variation, and this, as you go towards bottom, is actually depth in the sample. So a sample is a thick sample. You are actually seeing in an oblique manner. I know it becomes very difficult always whenever I have to explain this to someone. They are not used to. No one is used to see this kind of view where you are actually seeing into the depth of sample. So without doing any post processing, you are straight away looking into through the depth of sample, right? And this sweep action is due to translation stage. Because this is a very large volume scan, we had to make use of a translation stage in this case. But the main highlight of this result is that you can look through the depth of your sample when it is already scattering. This is not made transparent in any way. Okay. In a later version, you can see some much improved results. I'm again not talking much in detail what all improvements were made, but some optics were changed, resolution was improved, and so many things were corrected. So you can see this is 65 micron thick slice of same dentate gyrus region, and which is a hippocampal region of brain. And you can see all the neurons, dendrites, and even tiny structures. And you can see it throughout the section, which is 65 micron here. So again, if one had to do this on a confocal, you can never get this image of 65 micron thick section so easily. It will take lots of effort. Here is structural imaging example in zebrafish, which is another interesting organism. This is a fish sample here. Top is actually mouse, so don't worry about that. But here you can see the whole fish length. This is a very small fish. And by the way, the fish was alive when it was being imaged. The imaging does not harm a living organism. Okay, so the fish was alive, and after this, it was happy to swim around. Only during imaging, it has to be embedded in agar gel, and it can remain alive and get imaged. Okay. So here is whole fish. Here you can see how the neurons run through its length. And here is a very small segment of spinal cord. You can see the spinal column and how the neurons are spread like a circular fashion. And even some tiny axons are being visible there. Okay, this in fact will be probably my last slide. I just wanted to showcase the possibilities of different samples. Okay, this is the last slide in which I'm going to show something in which it is time lapse. So as I said, it's a live fish. And live fish in young age, they develop fast. So if someone has to do a developmental biology, it's very important to know how which region of the fish or any organism is developing. So here I took the same region, the tail region of fish, and saw how the spinal column is developing. So you can see those markers, they are showing live tracking as the fish is growing overnight. Okay. So this is 200-minute scan. I just turned on my microscope and went and home and slept. Next morning I came and it was done imaging, and I just plotted it after that. So you can get such high resolution imaging of how certain regions are developing in a living fish. And just for quoting a number, it makes use of only 100 microwatt of laser power. Okay, so it's not at all something where you are in a regime where you are going to burn the tissue or something. All of you know that how much will be 100 microwatt. It's just 0.1 milliwatt. It's very, very safe for any organism. So just some details are given. We are taking 400 planes every 2 minutes. And then laser goes off between every scan. All this is automated, and you can get this kind of imaging. Okay, I think that is all. I'll be very happy to take questions. Thank you.
Sir,
Yeah.
sir, how depth it can scan? Like,
Okay, so the depth basically depends on how scattering the samples are. Okay, I cannot quote exact values, but if you happen to look at the results, let's take something which is highly scattering. So brain is highly scattering for mice, and here in this particular data set you could see 65 micron, and so we had no problem in imaging up to 65 micron. Again, the other way I should probably quote this number is how much resolution you are interested in. Okay, because of scattering you will lose resolution. So at 65 micron depth we are able to get up to 4-5 micron resolution. Any feature which is up to 4-5 micron size you can definitely see. Okay.
yes.
One thing which I would like to again say here is the light sheet technique gets you better depth than any wide field microscopy. Okay, wide field microscopy always undergoes more scattering because whole of the sample is illuminated, right? Here you are just illuminating a particular plane of the sample which you want to image, and that by itself reduces the scattering effect. It does not reduce scattering, but it gives you better imaging because of you are not eliminating the whole sample. Yeah. Okay.
So, sir, like we are not eliminating the whole sample. Like the same concept comes in the dark field microscopy also.
Dark field, not so much, because dark field again you are eliminating a whole sample. It's not as much as bright field in terms of intensity, but if you don't illuminate sample you actually do not image, right? If you actually come to think about it. So dark field, if you light rays do not touch sample at all, you will not end up imaging. So in dark field what you do is you cut the light before putting it on camera, right? In your imaging arm you are cutting the light, but illuminating you are illuminating whole sample. Okay.
Sir,
So here you are controlling how much you illuminate the sample itself. You are illuminating with a phenomena called optical sectioning. Yeah.
sir, have it been tested on human? Like
No.
for human brain?
No. So humans are off limits for fluorescence microscopy. Because these are based on fluorescence phenomena, we cannot stain humans in any way, right? So if you had that application in mind, then no, fluorescence microscopy can never be used for humans. Human cells, yes, if you have extracted cells, then you can probably do it, but living humans, never.
Yeah. Okay, sir. Thank you, sir.
Nice talk,
Yeah.
Manish. Santosh here.
Yeah.
Probably if you go to the planet Pandora, you can see fluorescence. Fluorescence on humans. Yeah. Anyway, now
Okay.
towards the end of the talk, you presented this developmental imaging of the fish, and you mentioned
Right.
that it is GFP which is used for expressions. Now the question
Correct.
here is that you must have injected this green fluorescent protein, right? Injected into the fish. Now, how is it that it is preferentially imaging the neurons and just the neurons, and why
So
not any other?
These are transgenic fish. Nothing is injected. They are developed lines, and these lines of fish are developed in such a way that they show expression only in the neurons. So there are so many transgenic lines. Obviously, that forms the whole PhD research for so many researchers in neuroscience. It takes 10 years to develop a line which shows expression in only a certain region and certain set of neurons. So yeah, these are transgenic lines with expressing only neurons.
Only the neurons,
That's
and no
how
other
it is.
tissue is seen.
Yeah.
Okay, thank you.
Yes.
Sorry, Manish. nice presentation.
Yes, right.
And so I want to know, can you do multi-photon microscopy with this? So that your
Yes,
your,
so in
photo
fact,
bleaching will be less.
Yeah, I did. In fact, the Optics Express paper, I have not listed my papers here as such, but in 2018, the first paper in which I showed this result actually on the left side is I have shown a single photon, but it's possible with two photon light sheet as well. So two photon definitely penetrates deeper in the tissue. So you image sharper images at more depth with two photon light sheet. Yeah.
So you want to say something about this zebrafish? Why have you chosen and what are the advantages?
Zebrafish is a
Because
nice organism. Yeah, sorry.
no, there are many other model organisms, right? Zebrafish, C. elegans, then okay, a lot of them are there.
Right. So I consider myself as mostly for technology development. I was not doing anything to do with neuroscience as such, although I was in Department of Neurobiology. So one was practical reason was that our neighboring lab had zebrafish. That was the practical reason why we ended up imaging that and to help them in their research. Uh, as far as choosing any other model organism is concerned, it's fine. Zebrafish is transparent, so that makes it more attractive. So does C. elegans. Both are, I would say, equally interesting as far as optics is concerned, with similar scattering properties. Mice brain is challenging because of more scattering. So yeah, these are just two different domains as far as optics is concerned. From neuroscience perspective, yeah, depends on the problem being asked. Or from biology perspective, whichever model organism is of more interest, that's most welcome. Yeah.
Just a last question. So, why is this technique? Maybe this question is for the students. Why is this technique called a light sheet microscope?
Okay, so light sheet microscope, as I was kind of trying to explain in one of the slides in the beginning, was you create a sheet of light for illuminating your sample. Okay, so as there was a question about dark field, bright field, so that you will hear about so many microscopy techniques, right? Confocal also is there. Let's not go into that, but here in light sheet, you are exciting the fluorescence in your sample with a sheet of light. And sheet of light is nothing but you take a Gaussian beam, expanded Gaussian beam, and you, for example, take a cylindrical lens. Cylindrical lens is going to focus that Gaussian beam along a line, right? We think it is a line, right? But if you actually think about it in 3 dimensions, you will see that near the focal region, it is actually a sheet and not just a line. And that is what is actually going to optically section your sample. So when I say optical section, it's just that the fluorophores only in that region which lie within this sheet are going to fluoresce and emit photons. And those photons can be captured and used for imaging. So you are actually slicing your sample, not physically, but optically. And this slicing is due to a sheet of light, and therefore it is called light sheet microscopy. So you are focusing mainly on the way in which this sectioning phenomena is happening.
Then multiphoton probably will not work, I think. Yeah.
Multiphoton also, so multiphoton not in the
with the
way we are used to.
Yeah.
So multiphoton most people do by focusing with very high numerical aperture objective, forming a point focus. No, so when you do light sheet with multiphoton, you focus it not that sharply, and you can actually get elongated focus point. Like what is used is Bessel beam, for example, right? So if you use a Bessel beam with 2 photon excitation, then you will excite a thin pencil throughout the depth. Okay, and that is being used for in orthogonal direction to image. So then you have to
maybe it's more like a with some sort of wide field with high intensities.
No, so you form a pencil and then you sweep that pencil very fast in the sheet plane itself. Okay. So you basically end up using two galvo scanners. One galvo scanner which takes this pencil beam, a bezel beam, and sweeps it along the sheet direction, and thereby creating the sheet. And there is second galvo scanner which sweeps it along the z-axis. So you can take the whole sheet up and down based on that. So if anyone is interested, I'm happy to share papers. There are n number of papers on two photon light sheet microscopy. It's a very exciting field for sure. Yeah.
Thank you, Manish.
Sir, like,
Yeah.
is it possible to study about a genetic parameter using this technique?
So I am not qualified enough to answer that, but this is just a tool which can image fast. So if there is any application where you require rapid imaging in 3D, then go for light sheet. Okay. If it is something which requires very, very high resolution, but you can take hours to image, there are many other techniques which are way better than light sheet. Okay. But if at all you are trying to image something which is living and trying to get a very, very fast imaging in 3D, then light sheet is the answer. Okay.
Yeah. Okay, sir. Thank you, sir.
Yeah.
Thank you, Dr. Manish, for joining us in this lecture series, for sharing your expertise and enlightening us with your profound knowledge. Thank you very much.
Thank you.
Moving forward, I deem it my privilege to welcome Dr. Shailesh Srivastava, Associate Professor, Department of Physics, Sri Sathya Sai Institute of Higher Learning, who will be sharing with us about the various photonics research work that is going on here at our institute. Dr. Shailesh Srivastava completed his BSc, MSc and Ph.D. in physics from SSSIHL in the years 1987, 89 and 2001 respectively. Since 1989, for more than 2 decades, he taught physics at the +2 level at the Sri Sathya Sai Institute of Sri Sathya Sai Higher Secondary School, inspiring many students to take up physics for their higher studies. During this period, he also taught specialized photonics-based courses for the MSc and MTech students at SSSIHL. Currently, he works full-time at the Department of Physics, SSSIHL. He is a recipient of the Sai Krishna Award for Excellence in Teaching at the Sathya Sai Institute of Higher Learning and an academic gold medalist during his undergraduate studies at SSSIHL. He is listed as an educator in the Marcus Who's Who in the world. Dr. Shailesh also takes keen interest in guiding doctoral students in his areas of interest. Sir's research interests are in the field of fiber optic gyroscopes, resonators and sensors, optical coherence tomography, fiber lasers, ultrafast optics and non-linear optics. Apart from his passion for teaching and research, he is also a musician and lyricist par excellence and has composed and directed music for several events at SSSIHL. He is a mentor and a guide to all of us and has always inspired us. Without further ado, I now invite our very own Shailesh sir onto the dais. Dr. Shailesh Srivastava.
Om Shri Sai Ram. offering my pranams at Bhagwan's lotus feet. Respected elders and my dear brothers, I have just a few minutes to give you an overview of the work that is going on at SSSIHL in photonics, and therefore I will not be going into details of anything. Those students who are interested in knowing more can contact any of us, because this is not work which I am doing in particular. It is work which is being done by the entire department. We have a few faculty who are into photonics, and therefore you can contact them for more details. So primarily the photonics group here, I have kind of categorized it into 5 different divisions. One is optical sensors. It's a circle, you see, you can start anywhere. So optical sensors, they are ubiquitous all around the world. Almost in every domain you will have some sensor, and optical sensors are one of the things that we are looking at. Then you have optical materials, where we use photonics for characterization of optical materials, or there are people who make materials for optics. Then you have ultra-fast fiber lasers. Then we have some research going on in optical imaging. And then, because we have an MTech running in optoelectronics and communications, we also do some research in optical networking, optical communication side. We have in fact recently even signed an MOU with Infinera and University of Turin in Italy, where one of our students is working with them. So I'll give you a brief overview of each one of these. Wherever possible, you can, if you want to ask something, at the end we can take questions. So very recently, we have just this work of ultra-fast fiber lasers. It was always very fascinating. And as I told you that we had a department which was specializing in fiber optics and lasers since the 1980s. It was one of our dreams that we should be making our own lasers and with something new. So very recently we have just completed a Ph.D. The defense is about to take place. So technically the Ph.D. is not over, and in a few days I'm sure the Ph.D. will be granted. We have done some studies on ultra-fast pulse propagation in fiber lasers. You would have heard of solitons, pulses which can go in nonlinear media, especially in fibers, waveguide media, without distorting in time and in the frequency domain. We call them as solitons. So we can have lasers which give outputs in terms of solitons. And in recent times, last 10 years, we have another kind of regime of operation of lasers called the noise-like pulsed lasers. Actually, they always existed in some form, but nobody thought that there'll be any use for that. And when people were making lasers, fiber lasers, they would avoid getting those noisy outputs and then make them into solitons. And of late, people started investigating into the properties of these NLP lasers and found that they are very suitable for certain applications. So it's interesting that in our department, we also hit upon these NLP domain. And the two applications which noise-like pulse lasers really support, very interestingly, we are 3 students doing research, one on the left side and one on the right side, and one in the center. The center student is doing research on NLP-based fiber lasers, and its two applications are femtosecond micromachining, which the boy on the right side was working on, and optical coherence tomography, which another student is working on, that's in optical imaging. We have shown the first observation of Q-switched harmonic mode-locked noise-like pulses. It has not been reported earlier. In noise-like pulse lasers, this is the first observation. This has been published in Applied Optics. Q-switched lasers, all of you know, and when you have mode locking coupled with Q-switching, that's called Q-switched mode lock lasers. To get Q-switched mode lock lasers to lays in the harmonic regime is considered very difficult for a variety of reasons, which I will not go into. And we are happy that we could demonstrate a Q-switched harmonic mode-locked noise-like pulse regime. One of the applications of NLP lasers is in supercontinuum generation. Again, supercontinuum is very useful, as Brother Professor Santosh was just talking about white light probe. So supercontinuum is where you create something like a wideband light from a high power laser source. So that you can create all the way from visible to IR, white light and more, and people use that for spectroscopic applications. And again, there's one more new thing that we are actually aiming for this while doing this PhD, but we deviated as we started getting some new results with noise-like pulses. But now there's another student who has enrolled for PhD, and we are going into what we call dual comb spectroscopy. So we have what we call frequency comb. A few years back, we had Theodor Hansch from Germany getting a Nobel Prize for fiber laser frequency combs. You know, when a laser lasers, you have many longitudinal modes, and all the longitudinal modes, when in phase, when they get locked, they create a train of ultra-short pulses. In the frequency domain, it is like a comb of frequencies. Think of each of these fingers representing one frequency, and they're all in phase. You get an ultra-short pulse in the time domain. But you don't call that mode lock laser as a frequency comb, because it's very difficult to really make the comb, because you need to stabilize what we call the carrier envelope phase offset, which requires quite a bit of good work. And that's why the Nobel Prize for making the frequency comb. Now what actually happens in very simple sense is that even though the spacing between the tooth of these combs is fixed and you have a mode lock laser, in the frequency domain the entire comb is jittering, because the absolute value of frequency is not fixed, and that's because of dispersion in the cavity and then external perturbations, refractive index depending on this frequency. And therefore you need a lot of stabilization feedback techniques to keep the comb fixed. But just imagine the moment you have a comb, maybe ultra wide, spanning an octave in frequency, and if it is stable, it's not jittering at all, then you have a frequency standard for reference which is absolute, and you can use that for a variety of timing applications and frequency measurement applications. One of the persons who was marketing the Menlo Systems lasers that we have now, Menlo Systems is the company founded by Theodor Hansch. He was just giving a light talk telling that, you know, the world has benefited by so many $1 billion because of frequency combs, and that is because they are using varieties of timing applications where GPS timings are corrected by the frequency combs made by these by this company, and therefore he was telling that in terms of finance and stock markets, once you stabilize it by a microsecond better, you gain that many dollars. So we are looking at a new kind of frequency comb which can be made with much lower cost, where in a single laser cavity, if you have two laser outputs which are mode locked, then both of them represent two frequencies, and they are still not combs, they are just mode lock lasers. But just imagine, because they are coming from the same laser cavity, or it's a shared cavity, then it's very likely that all the external perturbations will be common to both. Then even though the combs, of course these two combs are overlapping in frequency domain, they have some common frequencies, but because they come from the same laser, the jitter within them is the same, all the external perturbations, and therefore the beat frequency between these two combs remains constant, unaffected by all other external perturbations. So a few years back, there's a lot of euphoria in making use of these frequency combs, single laser dual frequency combs, as very high standard, ultra high, fine resolution spectroscopy. So we were looking at that because we have some experience with fiber lasers, and we understand all of the nonlinear properties and the propagation fiber lasers. So we have already demonstrated a single laser dual mode locked output as part of this PhD, but we have not yet achieved coherency between those two. They should be coherent to interfere to get the beat frequency. The beat frequency will not change, and then you can use that in innovative ways. One of them that we are looking at is breath analysis for medical disease diagnostics. So where you just breathe into a device, and then it shows you whether you have that particular compound in your breath. Trace elements in your breath. So that's about ultra fast fiber lasers. Brother C.R. Santosh has been working in this area. This is just to say, we did it at a very low cost with all things that were already available in the lab, and some things which are lying around for 20 years. We picked out each one of those fiber optic components, etc. We have made our own autocorrelator, made our own spectrometer, and fully automated it using open source Scilab, not MATLAB or LabVIEW, but very simple Scilab applications. And this is what you are seeing is actually the spectrum of a soliton. This, where is the laser pointer? So on the right hand side is the soliton spectrum with Kelly sidebands, and the taken with our spectrometer, and you have also this one, which is the autocorrelation trace, and this is the first observation of the Q-switched harmonic mode lock noise-like pulses from the cavity. We have gone up to the 8th harmonic. Then the next one is sensors. Lab on a chip. See, sensors are a very general term, and you can have a wide variety of sensors. Of course, I should have written the photonic sensors, but in the other slide, photonics was there at the root. We have used femtosecond laser micromachining to micromachine waveguides and microchannels. This was done by the idea of making waveguides and microchannels in fused silica was done in Italy by our brother Krishna Chaitanya and his group. And then now we have applied this and our previous knowledge of fiber optics, something which was done when I was a student, bimodal sensors. So 2-mode fiber sensors, we have had a PhD on it in 1994 when professor was there, and now we have demonstrated very good sensitivity of the order of, already demonstrated 10⁻⁻⁷ in refractive index, And we plan to use in a few days' time, our brother Prajal will be going to IISc for doing work on medical diagnostics using these fused silica bimodal sensors on a chip. We call it lab on a chip, where we can demonstrate. We have also shown a new method of doing the sensing using CMOS cameras. We have done good amount of work with the plasmonic sensors, and chemistry department also we have collaborated, where they have been doing what we call SPCE, surface plasmon coupled emission of fluorescence. Our Muthu sir has worked in that area, and recently we have done a lot of Opti FDTD and COMSOL simulations of various resonant structures to do plasmonic sensing. Buried microchannels, we have also innovated during COVID time, because we did not have this expertise with HF. So HF is not so easy to handle, and we hit upon a new way to use KH and make rectangular microchannels, and that we are using in our lab on a chip. And we have also done work with the biology department for using the DREAM assay, as they call it, for bacterial activity monitoring in wastewater. Of course, we are trying to, we are not really doing fundamental physics, because being a private university, we naturally value every penny of the money that Swami has provided, and therefore we are trying to do things which will have short-term immediate benefits, and from that point of view, some of these things are good developments. This, we have made a device for wastewater characterization using simple photodiodes and Arduino integrated onto a chip. So this is just a basic idea of the lab on a chip work that is going on. The idea is, once we make a platform where you can integrate waveguides and microchannels, and then you can coat antibodies, then you could actually make a chip which will be able to sense, just like you have these commercial sugar sensors, blood glucose level. So you can just deposit one drop of some material, and then you can sense what you need to. This is another slide showing some of the COMSOL and FTDD simulations and the bimodal sensor that we have recently done. Then, talking of sensors, we have, I should of course tell that optical coherence tomography, which is part of the optical imaging modality, but we also used it for sensing, and we have done it for in vivo sensing of the vibrations of the tympanic membrane, and we have gone to 2 nanometer resolution. That means I can know whether the amplitude of vibration of the tympanic membrane is anything more than 2 nanometer. Our Denny sir has been working on this. He has done this work. He is teaching in Brindavan campus now. And that is with in vivo. It's quite challenging, because human beings can't stay stationary, you see. And that makes it very difficult. So we had to innovate some new methods to kind of track the membrane as it vibrates, so that relatively you get a kind of stable image, and then it is interferometric OCT, and therefore nanometer scale motion also causes blurring of the fringes. So that is one of the problems. With the static samples, we have gone up to 200 picometers of vibrometry resolution. Then we have another sensor, which is a fiber gyroscope. We have a totally, there are only 2 main categories of gyroscopes, which are the resonant gyroscopes using a ring resonator, and the IFOG, as we call it, which uses the Sagnac loop. And we have proposed a new gyroscope, which is made up of a ring resonator with a reflector. And this work, again, we have a few publications, And I don't know whether this simulation works here. Okay. This work was done by Brother Sumukh Nandan, who is currently teaching in the Brindavan campus. And what you see here, it's both of them actually. You know, he's actually rotating a table, and as the table rotates, the rotation rate is being plotted here. When he's doing slow rotation, this curve has less amplitude, and when he's doing fast rotation, the curve has more amplitude. And this is the reflectivity profile of the SCRWR as it goes, and when the reflectance becomes larger, it splits, and that's the fiber gyroscope work. And yeah, I think you can skip that. This is the surface plasmon coupled emission which Muthu sir has worked on, where you excite surface plasmons in fluorophores through the evanescent field coupling. Then we have materials, optical materials. We are primarily doing characterization of optical materials. We have recently set up an automated femtosecond Z-scan as part of an MSc project. Just this year we did it, automated femtosecond Z-scan. This you see a trace of closed aperture and open aperture Z-scan, and also we do time resolved femtosecond degenerate 4-wave mixing using the boxcar geometry, and that also we have done with a number of samples. So one can do time resolved studies, but primarily I am not, and we are the ones who have set up this. We are not from the not looking at the material aspect, but it was more from the device fabrication. But we have been collaborating with the chemistry people who synthesize new nonlinear materials, and then we look at their nonlinear properties and try to understand that along with them. Then optical imaging, this is the device which you see here is a portable, maneuverable optical coherence tomography, low cost. Normal optical OCT devices are 50 to 60 lakhs. Because of the swept source OCT, of course, the performance is very good, but we just wanted to look at, you know, every application possibly doesn't need an elephant. So why not have an OCT which can work at a much lower cost, but look at some niche applications which we can do. You're seeing here the tympanic membrane imaged in vivo of some volunteer. I think this one was Mr. Denny's own tympanic membrane, and we have here the what we call the malleus. The bone behind the tympanic membrane is also seen. Our original idea, we have not reached there because we went for a very low cost, and therefore the SNR is not that good to penetrate deep. We wanted to image the ossicles, that is the middle ear, stapes, malleus, incus, the three bones, and if I can tell whether the stapes is vibrating or not to the doctor, then without doing a surgery he can decide whether a surgery is required or not. Otherwise they have to operate and then look at whether the bone is stuck or the nerve is gone. And if the bone is stuck, he can just remove the bone and free it, and the person can hear again. He doesn't have to do surgery. Whereas if it's the nerve which is gone, even after he does surgery, he cannot do anything. So it's a wasted surgery, and therefore this was one of the ideas. We had to stop this work midway because COVID was hitting us, and the symptoms of this disease called otitis media are very similar to COVID. So 2 times we went to the hospital and came back, each time with one wave of COVID. That's because we are not really doctors experienced with handling those risks. But meanwhile, we went into other domains and we did OCT for angiography simulations, and we have shown, people have done angiography of blood to show blood rate flow, and most of them are doctors who are working, so they are not really knowing the physics behind it. So we did some simulations to show why a certain technique works that way. this is of course femtosecond micro machine, micro channel, 3D imaged using our OCT machine. You can show that video. There only. It was there. Oh. So there. That's a 3D. It's a cross channel which has been micro machined into fused silica and imaged by the OCT that we have developed. Then we have Raman microscopy as another work that is going on. Kumar sir is again into this Raman microscopy. They have done good work in collaboration with the bioscience department. This you see some Raman microscope images of the avascular necrosis of the bones. This is rheumatoid arthritis patients, and they have shown some correlation with some biomarkers. Muthu sir will tell you more about this. Then I think this work does not require any introduction. Many of you would have seen this. As Swami says, we do a lot of research, but very less of it really finally reaches applications in the real world. And we are very proud to say that, in our institute we have developed one such amazing instrument. And I think I will not talk about it because we have a beautiful video. Our Murli sir, Mr. Murli Ravi is along with Shiv Shankar Sai sir. They are the ones who have developed it, and another PhD is ongoing. Brother Sumukh has also worked partly on the fluorescence aspect. So it has come into photonics because they have added newly in the handheld dual mode of fluorescence imaging modality to help the doctors do surgery intraoperatively. They can help the doctor to locate cancerous cells so that they need not again operate and check whether these things are gone or not. We'll show you that video. Okay, these are some of the publications that we have done on many of these works. This is plasmonics, so just for your information. So this starts with, this is fiber laser, this is on lab on a chip sensor, this is Raman microscopy, this is OCT, and this is on plasmonic, surface plasmon coupled emission. This is on bacterial wastewater characterization. This is on gyroscope, again on gyroscope. This is just a sample. Vibrometry, and this is nonlinear optical material characterization, and this is again nonlinear optical material characterization. This again nonlinear optical material characterization. So these are some sample of the research works that are being done at SSSIHL. What I have not shown you here is the optical communication side, where now we are working on what we call the Gaussian noise model for modeling the activity in an optical, long haul optical network which is not dispersion compensated. When a network is not dispersion compensated, there will not be four-wave mixing. I mean, there will not be much four-wave mixing effects. And Infinera, and along with our brother Santosh, they are now currently working on this project. Apart from that, our MTech students have regularly published in IEEE ANTS conference on optical transport network and many such publications. You can show that video. We will end with this, and then we'll have the vote of thanks. So we will see this video on gamma camera, and I'm sure all of you will once again feel proud that, very recently also Kaushik, who is working on this gamma camera, he goes to this hospital in Bangalore, I'm forgetting the name, and they are doing surgeries live, and he says that the success rate till now they have done 8 patients and with 100% success. We'll now watch that video.
Surgical resection of cancer remains an important treatment modality. Despite advances in preoperative imaging, surgery itself is primarily guided by the surgeon's ability to locate pathology with conventional white light imaging. Intraoperative visualization of tumors may not only allow more complete resections, but also improve safety by avoiding unnecessary damage to normal tissue, which can also reduce operative time and decrease the need for second-look surgeries. Surgery is a primary mode of treatment for many malignancies. For example, 63 to 98% of patients with lung, breast, bladder, and colorectal cancer undergo surgery. The determination of tumor margins must often be done blindly, followed by frozen section pathologic analysis. The presence of residual tumor cells after resection is considered a strong predictor of tumor recurrence and therefore survival. Despite advances in preoperative imaging such as computerized tomography, CT, magnetic resonance imaging, MRI, and positron emission tomography, PET, surgical margin positivity rate has not changed significantly over the past several decades, with margin positivity rates of 15 to 60% across all cancers. Currently, the standard of care for achieving negative margins rests on visual inspection, palpation, and intraoperative histopathological analysis of frozen tumor margins, all of which have severe limitations. The naked eye is limited in its ability to detect small tumors. A number of non-optical imaging methods have been proposed during surgery. Typically, these methods are not targeted to the tumor per se, but rely on anatomic abnormalities to define the tumor, like the intraoperative CT and MRI. However, intraoperative systems are costly, complex, and require space. Moreover, their use interrupts the normal workflow of the surgical procedure, lengthening operative and anesthesia times. Hence, there is an increased need to have a small, handheld, and high-precision intraoperative sentinel lymph node navigational assistance using intraoperative probes. The group previously worked on developing a new-age portable gamma camera called SSSIHL, which revolutionized gamma imaging with patented high-resolution semiconductor detectors. This high-speed all-digital device can produce images 5 times higher in spatial resolution and speed, but it is 10 times lower in cost compared to commercially available models. This makes accurate diagnosis cheaper and more available to a common man. Clinical trials were performed with SSSIHL, and it produced concurrent results on all the subjects, thus proving the efficacy of SSSIHL. Now the team is working on the intraoperative probe called SSSIHL Torch. The young team at Sri Sathya Sai Institute of Higher Learning, Department of Physics, are working on inventing a new age device which can solve the issues faced by surgeons in this regard. The device proposes to have a nuclear imaging modality to provide post-operative validation along with fluorescence imaging for lymph node navigation, assisted by optical imaging to provide a frame of reference to the surgeon. The project is funded by the Department of Atomic Energy, Government of India. The students and the research scholars involved in this development offer this device Sai GC torch at the lotus feet of their divine founder, Chancellor Bhagavan Sri Sathya Sai Baba, and pray that many are benefited from this invention.
What I did not tell about SciGC is that proudly that it combines nuclear physics, photonics into one, and material science because of the detector, the CZT semiconductor based detector, and now the cesium iodide based detector which they are using. So material science, photonics and nuclear physics all at the intersection of it all, and because it integrates the electronics, VLSI technology, FPGA based automation and speed up. So it is like a full product which uses everything that we have at our university in the Department of Physics. And very proudly I will also say that all of these works and researches, that they're all by students of our university. They've all finished their masters in Prashanti Nilayam and then gone to do all these research works, which is again a very rare thing in many institutions, that the students have done their masters there and then continue for their PhD. So we pray to Bhagwan that we'll have more such students in the future. And again, as I see Professor standing here, I'm sure he'll feel very happy to see part of the dream that he had coming true. And as Professor N.K. Sundaresan, he'll also feel proud that the department where he spent 20 years of his time and energy has produced things which are worthwhile. Especially this last thing gives a lot of satisfaction because you can see its application during your own lifetime. Not that other science things don't have applications, but it takes time. So if I do the research, maybe my grandson or sometimes son will see the benefit. But here is somewhere where you can feel happy during your own lifetime. So thank you very much for your patient listening. Sai Ram.
Thank you, sir, for shedding light on the various photonics research activities that is going on in our institute. I'm sure this has motivated many of us here to undertake photonics as a career. Thank you, sir. As we come to an end, we are very grateful to have various experts in the field take out the time from the busy schedule and educate us about the various ongoing research works in photonics. We are very grateful to all the guest speakers today. I now call upon Shri Prajal Chhetri, Doctoral Research Scholar, Department of Physics, to propose the vote of thanks.
Sai Ram, offering my most humble pranams at the divine lotus feet of our most beloved Bhagwan, distinguished guest speakers, respected teachers, and my dear brothers. A loving Sai Ram to all. On behalf of the Department of Physics, Sri Sathya Sai Institute of Higher Learning, it gives me great honor and privilege to extend heartfelt gratitude to everyone who has contributed to the success of the second edition of Professor N.K. Sundaresan Memorial Lecture Series on Recent Trends in Photonics. Let us begin by expressing our deepest gratitude to Bhagwan Sri Sathya Sai Baba, the founder chancellor of our esteemed institution, for his divine guidance and blessings in all of our endeavors. A sincere appreciation goes out to the university's administration for their relentless efforts and active support in organizing these enlightening talks, which have been instrumental in fostering academic discourse and intellectual growth. Our heartfelt thanks extend to our distinguished speakers, beginning with Professor R. Gaurishankar, Dean of Academic Affairs, and Professor Pallav Kumar Barua, Dean of Sciences, whose inaugural addresses eloquently set the stage for the enlightening discussions that followed. We are also deeply grateful to Professor K. Srinivasan sir for his insightful reminiscences, providing us with a profound connection to the inception of the Department of Physics and the legacy of Professor M.K. Sundaresan. The invaluable contributions of our esteemed speakers, Dr. Saptarishi Chaudhary, Dr. N. Kamaraju, Professor R. Sai Santosh, Dr. Manish Kumar, and our very own Dr. Shailesh Srivastava have enriched our understanding of photonics and its diverse applications. Their expertise and passion for research have inspired us all. We must also extend our gratitude to Professor M.K. Sundaresan, whose enduring legacy continues to inspire students and researchers alike, propelling us towards excellence in the field of photonics. Special thanks are due to our campus director, Dr. R. Raghunath Sarma, for his unwavering support, as well as to our brother Raghuram for his technical assistance even on a holiday. The seamless live stream support provided by the multimedia department ensured that the lectures reached a wider audience, and we are grateful for that. We cannot overlook the dedication and hard work of our department teachers, whose tireless efforts in the past week have made this memorial lecture series indeed memorial. Last but not least, our sincere appreciation goes out to the attentive and engaged audience. Your participation and enthusiasm have made these sessions truly interactive and memorable. As we reflect on the enlightening discussions and insights shared throughout this memorial lecture series, let us remember the words, "In photonics, we illuminate not just the world around us, but also the boundless possibilities of the future." In conclusion, let us carry forward the spirit of Professor M.K. Sundaresan's legacy by pursuing excellence in research and academic endeavors. Thank you once again to everyone who has made this memorial lecture series a remarkable success. With this, we come to an end of yet another series of a wonderful lecture series. We will end this session with Mangala Arati. I request Dr. K. Vijay Sai, Head of Department of Physics, to offer Arati to Bhagwan. Sai Ram. ओम जय जगदीश हरे, स्वामी सत्य साई हरे, भक्त जना संरक्षक, भक्त जना संरक्षक, प्रति महेश्वर। ओम जय जगदीश हरे। शशिवदना श्रीकरा सर्वा प्राणपते, स्वामी सर्वा प्राणपते, आश्रित कल्पलतिका, आश्रित कल्पलतिका, आपद बांधवा। ओम जय जगदीश हरे। माता पिता गुरुदेवमु मरि अंत्रयो नीवे, स्वामी मरि अंत्रयो नीवे। नाद ब्रह्म जगन्नाथ, नाद ब्रह्म जगन्नाथ, नागेन्द्र शयन। ओम जय जगदीश हरे। ओंकार रूप ओजस्वी ओ साई महादेवा, सत्य साई महादेवा। మంగళహారతి అందుకో మంగళహారతి అందుకో మందరగిరిధారి ఓం జయ జగదీశ హరే नारायण नारायण ओम सत्यनारायण नारायण नारायण ओम नारायण नारायण ओम सत्य नारायण नारायण ओम सत्य नारायण नारायण ओम जय सद्गुरुदेवा नारायण नारायण ओम सत्य नारायण 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 ओम नारायण नारायण ओम सत्य नारायण नारायण ओम नारायण नारायण ओम जय सद्गुरुदेवा नारायण नारायण ओम सत्य नारायण 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 ओम नारायण नारायण ओम सत्य नारायण नारायण ओम सत्य नारायण नारायण ओम जय सद्गुरुदेवा ओम शांति 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 समस्तलोकाः सुखिनो भवन्तु समस्तलोकाः सुखिनो भवन्तु समस्तलोकाः सुखिनो भवन्तु ओम शांति 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 जय बोलो भगवान श्री सत्य साई बाबा जी की जय।